The universe is filled with vast structures, many of which we can only begin to understand. One of the most mind-boggling discoveries in recent astronomy is the Sloan Great Wall, a colossal cosmic formation that doesn't seem to fit within our current understanding of the universe's structure. Located in the constellation of Pisces, it is a massive galaxy filament stretching over 1.3 billion light-years, a size that challenges the traditional models of cosmic formation. This massive wall of galaxies is one of the largest known structures in the universe, and its discovery has raised important questions about the limits of cosmic expansion and the forces shaping the universe. Yet while it is massive, the Sloan Great Wall poses a paradox. Its sheer size and structure conflict with the general understanding of how the universe should work on a grand scale. How did something so large form? And what does it mean for the future of our galaxy and the universe at large? These are just a few of the questions we'll explore as we take a deeper look into this structure that doesn't quite fit. What is the Sloan Great Wall? The Sloan Great Wall was first identified in 2003 as a massive galaxy filament by the Sloan Digital Sky Survey, which aims to map the universe by cataloguing galaxies and their structures. Its discovery was not a result of a single observation, but a product of years of data gathering and analysis that finally allowed astronomers to realize just how large and significant this structure really is. Located about 1 billion light-years away, it spans a mind-boggling 1.3 billion light-years in length. This size makes it one of the largest known cosmic structures, and it's roughly 10 times the size of the previously largest known structure, the Hercules Corona Borealis Great Wall. Unlike other galaxy clusters and superclusters that appear scattered across the universe, the Sloan Great Wall is not just a random grouping of galaxies. It forms a massive, almost linear arrangement, linking together vast superclusters of galaxies. These superclusters themselves are tied by a web-like structure, often referred to as the cosmic web. But the Sloan Great Wall stands apart due to its immense size and coherence. It's more like a wall of galaxies than a scattered network. This uniqueness was part of what initially perplexed astronomers, as it went against the expectation that galaxies would be spread more evenly across the universe. In essence, the Sloan Great Wall is a large-scale structure, a cosmic filament that can be compared to the bones of the universe, connecting various clusters of galaxies. But it's not just the size that makes it important. The discovery of such a structure brought to the forefront critical questions about the way galaxies form and the forces driving their alignment in such an enormous and coherent structure. For a long time, it was believed that large-scale structures like the Sloan Great Wall were uncommon, and that the universe's overall distribution of galaxies should look more uniform. The Sloan Great Wall doesn't follow these assumptions, thus forcing cosmologists to revisit some of their core beliefs about the universe's formation and the factors that govern large-scale cosmic evolution. While it's tempting to compare the structure of the Sloan Great Wall to terrestrial phenomena, like mountain ranges or continents, these comparisons fall short. The enormity of the wall far surpasses anything on Earth, making it impossible to truly comprehend its scale in relatable terms. If you were to place the entire length of the Sloan Great Wall in context, it would take light over 1.3 billion years to travel its full length, an incomprehensibly vast period in human terms. Yet even with this immense size, it's only a small part of the bigger picture of cosmic structures that we are just beginning to understand. The discovery of the Sloan Great Wall also raised significant questions about the cosmic voids, vast regions of space that appear to be nearly empty of galaxies. The existence of such a dense structure in the middle of an otherwise expansive universe adds another layer of complexity to our understanding of cosmic formation. Some believe that the Sloan Great Wall is part of an even larger structure that spans much farther across the universe, suggesting that the very fabric of the universe may be more intricately connected than previously thought. Understanding what the Sloan Great Wall is and why it exists where it does is essential to understanding how galaxies and large-scale structures form. As we continue to explore the structure, It offers us clues not only about the forces that shaped our universe in the past, but also about the way it might evolve in the future. It's one of those cosmic structures that raises more questions than answers, and studying it will be crucial for astronomers as they work to map the universe's full complexity. Mapping the universe, a breakdown of cosmic structures. To understand the significance of the Sloan Great Wall, it's essential to first consider how we map the universe. Astronomy, particularly the study of large-scale cosmic structures, has become increasingly sophisticated over the past few decades thanks to advanced telescopes, surveys, and simulations. Historically, astronomers relied on visual observation, with early maps of the universe drawn based on the visible light coming from stars and galaxies. But today, with the advent of tools like the Sloan Digital Sky Survey, SDSS, astronomers have a much clearer and more detailed picture of the universe's structure. The Sloan Digital Sky Survey, initiated in the early 2000s, has provided a comprehensive map of the universe, capturing detailed images and spectra of millions of galaxies. This survey is unique in its scope, using an array of specialized instruments to observe the sky in a way that allows scientists to study the distribution of galaxies across the entire observable universe. By analyzing the light emitted from distant galaxies, astronomers can determine their distance, speed, and composition, creating a three-dimensional map of the cosmos. The universe, once thought to be more or less homogeneous, turns out to be far more structured than initially believed. The cosmic web, a term used to describe the large-scale structure of the universe, consists of vast interconnected regions of galaxies that form filaments, clusters, and walls, with enormous voids in between. These filaments connect large groups of galaxies into vast structures that can span hundreds of millions of light-years. The Sloan Great Wall is one of the largest and most striking of these filaments. But how do we differentiate between a cluster, a wall, and a void? A galaxy cluster is a dense grouping of galaxies bound together by gravity. Clusters are the largest gravitationally bound structures in the universe, and they often serve as the intersection points of the cosmic web. Walls, like the Sloan Great Wall, are similar in that they are enormous clusters of galaxies, but they stretch across even larger distances, creating vast sheets that can span 1 billion light-years or more. Between these walls are the voids, immense regions of space with very few galaxies, representing the empty areas of the cosmic web. In mapping these structures, astronomers use both direct observation and computational models. Observations from telescopes like SDSS give them a snapshot of the universe's large-scale structure. However, it's the computer simulations that help make sense of this vast data. These models simulate how galaxies form, interact, and evolve over cosmic timescales. By comparing the observed data with the results of these simulations, astronomers can refine their understanding of the universe's fundamental structure and the forces that shape it. The discovery of the Sloan Great Wall was possible because of these advances in both observational and computational techniques. When astronomers first noticed the unusual concentration of galaxies, they used these tools to measure the structure's scale, shape, and position. They confirmed that it was not just a random collection of galaxies, but a coherent, large-scale structure that stretched across a significant portion of the cosmos. By comparing it with similar but smaller structures, they concluded that the Sloan Great Wall was an outlier, a massive wall of galaxies that didn't quite fit the expected patterns of the cosmic web. What's particularly intriguing about the Sloan Great Wall is its position in the universe. Unlike other large-scale structures, it doesn't sit at the intersection of several filaments. Instead, it appears to be an isolated, linear structure, a wall that doesn't quite match the standard distribution of galaxies. This raises important questions about how the universe forms its structures. If the Sloan Great Wall is indeed unique, what does this imply about the fundamental processes that govern galaxy formation and the large-scale structure of the universe? The existence of the Sloan Great Wall is not an isolated phenomenon. There are other similar structures in the universe, such as the Hercules Corona Borealis Great Wall, which was discovered in 2013 and is currently thought to be the largest known structure in the observable universe. However, what sets the Sloan Great Wall apart is not its size, but rather its location and the way it stretches across space in a nearly continuous line. These unusual alignments defy the expectations set by the standard models of galaxy formation, which predict a more random distribution of matter across the universe. To explore this further, scientists continue to use advanced simulations to model the formation of these cosmic walls. These simulations attempt to recreate the conditions of the early universe, where galaxies formed from tiny fluctuations in the density of matter. By studying how these fluctuations evolved under the influence of gravity, astronomers can better understand how massive structures like the Sloan Great Wall come into being. Current models suggest that such structures may be the result of early cosmic conditions that created dense pockets of matter, which were then shaped and stretched over billions of years by gravity. One of the most significant aspects of these simulations is the role of dark matter. While we can't directly observe dark matter, its gravitational effects are evident in the formation of large-scale structures. Dark matter clumps together in galaxies and galaxy clusters, providing the gravitational framework around which normal matter, composed of visible stars and galaxies, can accumulate. This means that dark matter is not just a passive force in the universe, but an active participant in shaping the very fabric of the cosmos. The Sloan Great Wall, like many other large-scale structures, likely owes much of its formation to the presence of dark matter. In the next chapters, we will dive deeper into the dark matter connection and discuss its role in the formation of large-scale structures. But for now, understanding how these cosmic structures are mapped, observed, and analysed gives us crucial insight into the nature of the universe itself. The Sloan Great Wall is just one example of the complex, dynamic system that governs the large-scale distribution of matter in the cosmos. Its discovery is a testament to the power of modern astronomy and computational modelling, and it has opened up a host of new questions that will shape the future of our understanding of the universe. The largest known structure in the universe. When the Sloan Great Wall was first identified in 2003, it quickly captured the attention of astronomers and cosmologists around the world. At a length of 1.3 billion light-years, it was soon recognized as one of the largest known structures in the universe, and still holds that title today. But what makes the Sloan Great Wall so extraordinary is not just its size, but the fact that it challenges many long-held assumptions about how galaxies and large-scale structures should behave in the cosmos. The sheer size of the Sloan Great Wall alone is enough to give us pause. To put it into perspective, the Milky Way itself, our home galaxy, is about 100,000 light-years across, meaning that the Sloan Great Wall spans a distance that is 13,000 times the size of our galaxy. This makes it not just a remarkable discovery, but a structural anomaly that forces scientists to rethink the distribution of galaxies on the larger scales. Galaxies like our own Milky Way are typically part of larger cosmic structures, which astronomers refer to as superclusters. These superclusters are vast collections of galaxies that are bound together by gravity, forming the building blocks of the universe. The Sloan Great Wall, however, doesn't behave like a typical supercluster. It is a massive wall of galaxies, stretching in a near-linear formation, which makes it different from the more randomly distributed galaxy clusters that make up most superclusters. One of the most surprising aspects of the Sloan Great Wall is that it does not sit at the intersection of several galaxy filaments, as many other large structures do. Instead, it appears as a single, distinct, and largely uninterrupted wall of galaxies. The fact that a structure of this size and shape could exist in the universe forces scientists to reconsider their understanding of how these large-scale cosmic structures form. The cosmic web, which is the general term used to describe the vast network of galaxies, clusters, and filaments that span the universe, was once thought to be fairly uniform in its distribution. However, the Sloan Great Wall stands out as an anomaly. Its linearity and scale are unprecedented. A key aspect of understanding the magnitude of the Sloan Great Wall is recognizing that it is not just an arbitrary grouping of galaxies. Rather, it is an example of galactic alignment, where multiple galaxies are arranged in a highly specific formation. The gravitational forces at play between the galaxies within the wall are immense, and the interactions between these galaxies likely influence their motion over billions of years, leading them to coalesce in such a massive structure. In fact, the Sloan Great Wall is part of a larger phenomenon known as the Laniakea supercluster, which is a vast collection of galaxies that includes not only the Milky Way, but also the Andromeda Galaxy and hundreds of other galaxies within our local universe. The Sloan Great Wall, while not the central feature of the Laniakea supercluster, is nonetheless one of its most striking members. The scale of the structure demands that scientists think on a much larger scale than ever before. One of the factors that has made the Sloan Great Wall such a challenging object of study is its size. Its sheer scale makes it difficult to study in detail with existing telescopes. Even though astronomers have now mapped a significant portion of the structure, much of it remains outside the reach of current observational technologies. The discovery of such a massive structure was made possible through advanced cosmic surveys and powerful instruments like the Sloan Digital Sky Survey, SDSS, which have allowed scientists to map the positions and velocities of hundreds of thousands of galaxies in incredible detail. However, the full extent of the Sloan Great Wall, like many large-scale structures in the universe, cannot yet be fully captured in a single study. The Sloan Great Wall is not alone in terms of its size. There are other massive structures in the universe, such as the Hercules Corona Borealis Great Wall, which is currently considered the largest known structure and spans over 10 billion light-years. However, the Sloan Great Wall remains one of the most significant discoveries because it highlights how these vast structures are organized on scales that are difficult to comprehend. It also poses challenges to our understanding of dark matter and dark energy, as these invisible forces are thought to play a crucial role in the formation of such large structures. Dark matter, in particular, has been a key player in the formation of these massive structures. It is believed to be the scaffolding upon which visible matter, like stars and galaxies, is anchored. The distribution of dark matter in the universe influences the way galaxies form and group together. The Sloan Great Wall's existence suggests that dark matter might not be as evenly spread as previously thought, and that large-scale gravitational interactions could lead to the formation of these immense walls of galaxies. In the future, as astronomical technology continues to advance, it is likely that we will gain a better understanding of the true nature of the Sloan Great Wall. Next-generation telescopes, such as the James Webb Space Telescope, could provide new insights into the structure of this wall and its place in the larger cosmic web. As we develop more powerful methods of exploring the universe, we will continue to learn more about the forces that shape these vast cosmic structures and the role they play in the ongoing evolution of the universe. But for now, the Sloan Great Wall stands as a testament to the complexity and grandeur of the universe. It challenges our existing models of cosmic structure and reminds us of just how much we still have to learn about the universe in which we live. Mapping cosmic structures, how we found the Sloan Great Wall. To fully appreciate the significance of the Sloan Great Wall, it's crucial to understand how astronomers detect and map these vast cosmic structures. Our understanding of the universe's large-scale architecture has only become possible with advancements in observational technology, particularly large-scale sky surveys, like the Sloan Digital Sky Survey, SDSS. Before these kinds of surveys, astronomers were largely limited to mapping individual galaxies, star clusters, and nebulae. But the Sloan Digital Sky Survey, launched in the early 2000s, revolutionized how we observe and categorize the universe. By using a dedicated telescope array and an advanced spectrograph at the Apache Point Observatory in New Mexico, SDSS captured images and spectra of millions of galaxies, stars, and other celestial objects, revealing the true complexity of the universe. One of the SDSS's most powerful tools is its ability to measure the redshift of galaxies. Redshift refers to the phenomenon where the wavelength of light from an object stretches as it moves away from an observer. This stretching happens because the universe itself is expanding, causing galaxies to move away from us at increasing speeds. By measuring the redshift of galaxies, astronomers can calculate their distance and motion, allowing them to map galaxies across vast regions of space. Through the SDSS, astronomers were able to detect an unexpected pattern. Vast clusters and filaments of galaxies appeared to be aligned in a way that suggested large-scale structure beyond what was previously anticipated. When the data from the survey was analysed, researchers noticed an immense structure stretching across more than 1 billion light-years. This turned out to be the Sloan Great Wall. The discovery of the Sloan Great Wall was not just a simple finding of a large cluster of galaxies. It represented a breakthrough in our understanding of cosmic structure. Unlike most galaxy clusters, which tend to be scattered more randomly across space, the Sloan Great Wall appeared to be a cohesive, linear formation, something that had not been predicted by existing models of cosmic structure. This forced scientists to re-examine how galaxies group together and interact, leading to new theories about the role of dark matter and cosmic expansion in the formation of large-scale structures. The mapping process that led to the identification of the Sloan Great Wall was also crucial for understanding the cosmic web, the vast, interconnected network of galaxies and galaxy clusters that forms the large-scale structure of the universe. While previous models suggested that the universe was a relatively smooth and uniform expanse of galaxies, the SDSS data showed that galaxies are not evenly distributed. Instead, they are found in vast threads or filaments that stretch across the universe, with large voids in between. The Sloan Great Wall is one of the largest of these filaments, spanning across billions of light-years and connecting multiple clusters of galaxies. Understanding the methodology behind the discovery helps highlight just how extraordinary the Sloan Great Wall is. Astronomers didn't just stumble upon this massive structure. It was through detailed mapping and data analysis that they pieced together the clues. The survey's comprehensive approach to capturing both images and spectra of galaxies allowed astronomers to understand not just where the galaxies were, but how they moved relative to each other, revealing the underlying structure of the universe. A critical aspect of this process was the use of three-dimensional mapping. Rather than merely observing galaxies in 2 dimensions on the sky, the SDSS allowed astronomers to create a 3-dimensional map of the universe. This map could not only tell them the position of galaxies in space, but also provide insight into their motion, allowing them to discern patterns in how galaxies were distributed. It was this 3D mapping that revealed the Sloan Great Wall in such incredible detail, showcasing the vast network of galaxies forming an interconnected wall across the cosmos. The SDSS team utilized an innovative method of statistical analysis to validate their findings. When they noticed the alignment of galaxies in a linear fashion, they ran simulations to see if this alignment was just a random occurrence. The results showed that such a structure, with its scale and coherence, was highly unlikely to appear by chance. The simulation supported the idea that the Sloan Great Wall was a legitimate structure, not just an outlier or anomaly in the data. This discovery also led to further questions. Why does the Sloan Great Wall exist in the way it does? How did it form, and what forces have shaped it over billions of years? These questions open new avenues of research into the role of dark matter in galaxy formation and the cosmic forces that influence large-scale structure. The structure of the Sloan Great Wall has sparked debates about the uniformity of the universe and whether other similar structures might exist beyond our current observational reach. The Sloan Digital Sky Survey was not a one-time effort, but a continual mission. The data gathered over the years has allowed astronomers to track the movement of galaxies over time, improving our understanding of the dynamics that shape these vast structures. The continuing work of SDSS and other surveys is crucial to further our understanding of not only the Sloan Great Wall, but the entire cosmos. By cataloguing more galaxies and improving the precision of measurements, scientists will eventually be able to create even more detailed maps, revealing the full complexity of the universe's large-scale structure. As astronomers continue to study the Sloan Great Wall, the lessons learned from this discovery will reshape our understanding of cosmic structure. The insights gleaned from the SDSS will likely continue to influence the way we think about galaxies and their interactions for years to come. The discovery of the Sloan Great Wall. In 2003, a team of astronomers working with the Sloan Digital Sky Survey, SDSS, made an unexpected and groundbreaking discovery: the Sloan Great Wall. This monumental cosmic structure, stretching over 1.3 billion light-years, quickly became one of the most significant findings in the field of astronomy. It stands as one of the largest known objects in the observable universe, and its discovery forced scientists to rethink their models of how galaxies and larger structures form in the cosmos. The discovery came as a result of galaxy surveys, which had been ongoing for some time. Astronomical surveys like the SDSS had already mapped thousands of galaxies, creating the most detailed 3D maps of the universe ever made. These surveys helped astronomers identify the structure of the universe on a smaller scale, cataloguing galaxies by their size, distance, and other properties. But when the Sloan team was analysing data in the Northern Hemisphere, they identified a large filamentary structure that was unlike anything anyone had seen before. This structure was vast, made up of countless galaxies, and it seemed to stretch across space in a way that suggested a level of organisation not previously expected in the universe. The Sloan Great Wall defied expectations. While scientists had theorised about large-scale cosmic structures like galaxy clusters and superclusters, the Great Wall was something entirely different. It wasn't just a collection of galaxies in a general region, it was a long, linear formation that stretched across a vast section of the universe. It was something larger, more complex, and more interconnected than anything previously known. Its discovery marked a turning point in our understanding of the universe's large-scale structure. Before the discovery of the Sloan Great Wall, the dominant theory about the distribution of galaxies in the universe was that they were spread relatively evenly across space. While galaxies tend to group together in clusters, the overall pattern was expected to be more or less uniform. But the Sloan Great Wall introduced a level of complexity to that model. The wall was not only a giant filament of galaxies, but also part of a much larger cosmic web. This web consists of vast filaments, clusters, and voids, regions where galaxies are sparse or absent. The Great Wall was a key feature of this web, showing that the universe was far more organised and structured than anyone had anticipated. The wall itself is essentially a cosmic filament made up of a vast number of galaxies and other forms of visible matter. It is connected by an intricate network of dark matter, which makes up the majority of the wall's mass. Dark matter, although invisible, exerts a gravitational pull that affects the movement of galaxies and other cosmic objects. This makes it an essential component in the structure and dynamics of the Sloan Great Wall. It holds the galaxies together and provides the necessary gravitational influence for the wall to maintain its shape. To fully grasp the significance of this discovery, it is important to understand the scale of the Sloan Great Wall. Its size and vastness can be difficult to conceptualize. To put it into perspective, it is nearly 1,000 times the size of the Milky Way, our home galaxy. The Milky Way is a spiral galaxy with a diameter of about 100,000 light-years. Yet the Sloan Great Wall is 1.3 billion light-years long. That's over 13 million times larger than the Milky Way. To even reach the edge of this structure, you would need a spacecraft capable of travelling at the speed of light for more than 1 billion years. This immense scale dwarfs anything in our galaxy and makes the Sloan Great Wall not only a physical marvel, but also an astronomical enigma. The discovery of the Sloan Great Wall had immediate and profound consequences for the field of cosmology. Prior to its discovery, scientists had assumed that the universe's large-scale structure was a lot more random and scattered. Galaxies were expected to be distributed more or less evenly across space, with some areas having more galaxies than others. But the Sloan Great Wall's sheer size and organisation challenged that model. Instead of a homogeneous distribution, the universe seemed to have large-scale structures, much like a network or web, with galaxies tied together through gravitational attraction and dark matter. The existence of such a large, interconnected structure called into question the earlier assumptions about the formation and distribution of galaxies. The discovery also had significant implications for our understanding of dark energy. Dark energy is the mysterious force that is causing the accelerated expansion of the universe. It was first discovered in the late 1990s and has since become a cornerstone of modern cosmology. While dark matter was already known to exist, dark energy was a much more elusive concept. The Sloan Great Wall's discovery raised new questions about the influence of dark energy on the formation of cosmic structures. Could dark energy be responsible for the way structures like the Sloan Great Wall formed? Or was it simply the result of gravitational forces acting over billions of years? One of the most significant consequences of the Sloan Great Wall's discovery was that it encouraged astronomers to take a closer look at the role of galactic filaments in the overall structure of the universe. Galactic filaments are massive structures made up of galaxies and dark matter that stretch across vast regions of space. They connect smaller clusters and form the backbone of the cosmic web. The Sloan Great Wall, as one of the largest known filaments, served as a critical point of reference for understanding how galaxies are connected and distributed on the largest scales. Astronomers began to rethink the way galaxies form and interact. The Sloan Great Wall provided evidence that cosmic structures are not only influenced by gravity, but also by the larger forces at play in the universe, such as dark energy and dark matter. The wall's formation was likely driven by the gravitational attraction of dark matter, which caused matter to clump together in a vast organised structure. This process, known as cosmic structure formation, takes place over billions of years as matter in the universe accumulates, creating galaxies, clusters, and filaments. In addition to its role in cosmological models, the Sloan Great Wall has also become an important target for future observational studies. As our technology continues to improve, astronomers are eager to gather more data about this colossal structure. New telescopes, such as the James Webb Space Telescope, JWST, and upcoming radio observatories, will allow astronomers to observe galaxies and cosmic structures with unprecedented detail. These instruments will help us better understand the evolution of the Sloan Great Wall and its role in the formation of the cosmic web. Furthermore, the Sloan Great Wall will continue to be a subject of interest for cosmological simulations. These simulations model the behaviour of galaxies and large-scale structures over time, and they rely on observations like the Sloan Great Wall to refine their predictions. As we continue to study the wall and similar structures, we will be able to better understand the forces that shape the universe, from the interactions between galaxies to the role of dark matter and dark energy. In conclusion, the discovery of the Sloan Great Wall has fundamentally altered our understanding of the universe's large-scale structure. This massive cosmic feature has reshaped our models of galaxy formation and has expanded our knowledge of the cosmic web. The wall's immense size, organisation and connection to dark matter and gravity have forced scientists to reconsider the basic assumptions about how the universe is structured. As we continue to study the Sloan Great Wall with new technologies and simulations, we will unlock further mysteries of the cosmos and perhaps uncover even larger structures waiting to be discovered. Understanding the structure of the universe. The cosmic web is a term used to describe the large-scale structure of the universe, consisting of vast filaments of galaxies, clusters, and voids that stretch across the observable cosmos. It represents the fundamental organization of matter in the universe, revealing how galaxies and clusters are connected by a network of invisible gravitational forces. The Sloan Great Wall, as one of the largest known structures in the universe, is an essential part of this cosmic web, and its existence forces us to reconsider our understanding of how galaxies are distributed and how large-scale structures form. The concept of the cosmic web was first proposed in the 1980s when astronomers began to realize that galaxies are not distributed randomly across the universe. Instead, they are found in vast, interconnected filaments that resemble a giant web. These filaments connect large groups of galaxies into clusters, while between them lie voids, massive regions of space with very few galaxies. This arrangement is not only visually striking, but also tells us a great deal about the forces that shape the universe. One of the key insights from the discovery of the cosmic web is the role of gravity. Gravity is the force that binds galaxies together and shapes the large-scale structure of the universe. While gravity is relatively weak on small scales, it becomes immensely powerful when acting on the vast number of galaxies in a cluster or filament. Over billions of years, gravity causes galaxies to clump together, forming the dense, interconnected filaments we see today. These filaments are thought to have formed from small density fluctuations in the early universe, soon after the Big Bang. In the very early universe, matter was nearly evenly distributed, with only tiny variations in density. However, these small fluctuations were enough to allow gravity to pull matter together over time. As the universe expanded and cooled, these fluctuations grew, eventually forming the vast structures that make up the cosmic web. At the center of each filament lies a galaxy cluster, a dense concentration of galaxies bound together by gravity. The Sloan Great Wall is one of the largest and most prominent examples of this type of structure, a wall of galaxies that stretches across 1.3 billion light-years. But the Great Wall is not an isolated feature. It is part of a larger network of structures that make up the cosmic web. These walls, filaments, and voids are scattered throughout the universe, and they define the overall large-scale distribution of galaxies. While gravity is the primary force behind the formation of the cosmic web, dark matter plays an essential role as well. As we've seen in earlier chapters, dark matter is an invisible substance that doesn't interact with light or other forms of electromagnetic radiation, but it exerts a powerful gravitational pull. In fact, dark matter makes up the vast majority of the mass in the universe. It provides the gravitational framework upon which visible matter, such as stars, gas, and galaxies, accumulates. Without dark matter, the cosmic web as we know it would not exist. Dark matter acts as the scaffolding for the cosmic web, providing the necessary gravitational pull to form the large-scale structures we observe. The cosmic web is not static, it is constantly evolving. Galaxies within filaments move toward one another over time, forming clusters and superclusters. These structures grow and merge, shaping the universe's overall evolution. The Sloan Great Wall itself is a product of this process, an incredibly massive structure that has formed over billions of years through the accumulation of galaxies in a specific region of the universe. But the cosmic web is not just about galaxies. It also provides insight into the structure of the universe on even larger scales. The voids in the cosmic web, which occupy vast regions of space between filaments, are equally important to our understanding of the universe. These voids are not empty, but rather contain a very low density of galaxies and matter. They are often thought of as the empty spaces between the walls and filaments, but they are just as essential to the universe's overall structure as the filaments themselves. The interactions between the galaxies in the filaments and those in the voids help shape the large-scale dynamics of the universe. The discovery of the Sloan Great Wall provides further evidence of the intricate and interconnected nature of the cosmic web. While it is an outlier in some ways, its existence shows that the universe is far more structured than we once thought. Instead of a random distribution of galaxies, the universe is organized into vast networks of filaments, walls, and voids that are shaped by gravity and dark matter. The Sloan Great Wall is a key piece of this puzzle, and its study will help astronomers better understand how these structures form, how they evolve, and how they affect the overall dynamics of the universe. As we continue to study the cosmic web, new discoveries will likely provide even more insights into the formation and evolution of the universe. While the Sloan Great Wall is one of the largest and most significant structures known, it is far from the only one. There are likely many other similar structures scattered throughout the cosmos, some of which remain undetected due to the limits of our current observational technology. The ongoing work of astronomers and cosmologists will continue to expand our understanding of the universe's large-scale structure, and the Sloan Great Wall will remain a central focus of this research. The cosmic web and its role in structure formation. The discovery of the Sloan Great Wall has provided astronomers with a new understanding of how galaxies are organized across vast distances. The concept of the cosmic web is central to this understanding. This web-like structure, made up of enormous filaments of galaxies and vast cosmic voids, defines the large-scale architecture of the universe. The cosmic web is not just a random arrangement of galaxies, but a highly structured and organized network that has evolved over billions of years. Understanding the formation and role of this web is crucial for understanding the nature of large-scale cosmic structures, including the Sloan Great Wall. The cosmic web is composed of three primary components: filaments, galaxy clusters, and voids. The filaments are vast, thread-like structures that stretch across the universe, connecting clusters of galaxies. These filaments are the largest known structures in the universe and are composed of galaxies and dark matter. They form the spokes of the cosmic web, linking the smaller galaxies and clusters together. The galaxy clusters, which are dense regions of galaxies bound together by gravity, sit at the intersections of these filaments. Finally, the voids are the empty spaces between the filaments, containing very few galaxies and making up about 80% of the volume of the universe. The formation of the cosmic web can be traced back to the early universe, shortly after the Big Bang. Initially, the universe was filled with a nearly uniform distribution of matter and radiation. However, small fluctuations in the density of matter caused by quantum instabilities began to grow over time. These fluctuations created areas of slightly higher density where gravity began to accumulate matter. Dark matter, which is invisible but makes up about 85% of the universe's mass, played a key role in this process. Dark matter clumps together due to gravity, forming the skeleton of the cosmic web. Normal matter, in the form of gas and eventually galaxies, accumulated around these dark matter clumps, forming the filaments that make up the web. The process of galaxy formation is deeply intertwined with the cosmic web. As the universe continued to expand and cool, the clumps of dark matter and gas began to collapse under their own gravity, eventually forming galaxies. These galaxies, in turn, were drawn into larger clusters and superclusters, creating the complex network of structures that we see today. The formation of the Sloan Great Wall is a direct result of these processes. It is a massive filament of galaxies that has formed along one of the largest threads in the cosmic web. One of the key insights from studying the Sloan Great Wall is the realization that large-scale structures like it are not static. The cosmic web is constantly evolving. Galaxies within the filaments are not simply sitting in place, but are moving and interacting with one another. These interactions can lead to the formation of new galaxies, the merging of existing ones, or the complete destruction of galaxies. For example, galaxies within the Sloan Great Wall may be gradually drawn toward each other, eventually merging into larger galaxies. The gravitational forces at play in such massive structures are immense, and they drive the evolution of the entire cosmic web. The dynamics of the cosmic web are also influenced by the expansion of the universe. Since the Big Bang, the universe has been expanding, with galaxies moving away from each other as space itself stretches. This expansion has caused the cosmic web to grow larger over time, with the filament stretching across increasing distances. However, this expansion is not uniform. In some regions, the gravitational pull of dark matter and galaxy clusters is strong enough to counteract the effects of expansion, leading to the formation of dense structures like the Sloan Great Wall. In other regions, the expansion of the universe is causing galaxies to move farther apart, creating vast voids. The study of the cosmic web and its role in structure formation is still ongoing. While much has been learned in recent decades, there is still much we don't know about how these large-scale structures evolve. One of the major challenges is understanding the role of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark energy is thought to make up about 68% of the total energy in the universe, but its exact nature remains unknown. It is believed that dark energy could play a significant role in shaping the future of the cosmic web by influencing the rate at which galaxies and filaments expand. Another challenge is the lack of direct observation of the cosmic web itself. While astronomers have mapped the distribution of galaxies and clusters, much of the cosmic web is invisible to traditional observation methods. The majority of the matter in the web is dark matter, which does not emit light or interact with electromagnetic radiation. This makes it difficult to observe directly. However, astronomers have developed techniques like gravitational lensing to indirectly study dark matter and the structure of the cosmic web. Gravitational lensing occurs when the gravity of a massive object bends the light from objects behind it, allowing astronomers to map the distribution of dark matter and galaxies. Despite these challenges, the study of the cosmic web and structures like the Sloan Great Wall is advancing rapidly. New surveys and observatories, such as the James Webb Space Telescope, are expected to provide even more detailed maps of the universe's large-scale structure. As technology continues to improve, we will likely gain a better understanding of how the Sloan Great Wall fits into the larger cosmic web, and what its formation can tell us about the evolution of the universe. The role of dark matter in the formation of the cosmic web cannot be overstated. Without it, the structure of the universe would be vastly different. The vast filaments and clusters that make up the cosmic web would not exist in the same way, and the universe would lack the level of organization and structure we observe today. The Sloan Great Wall, as one of the most striking examples of this structure, serves as a reminder of the importance of dark matter in shaping the cosmos. Here are the three expanded sections with the new additions integrated. The mystery of the wall's formation. One of the most fascinating aspects of the Sloan Great Wall is the mystery surrounding its formation. While we have a general understanding of how large-scale structures like the wall come into being, the specifics of how such a massive and well-defined feature formed remain elusive. The wall's enormous size and linear shape set it apart from other cosmic structures, raising several questions about the processes that led to its creation. At its core, the Sloan Great Wall is part of a larger cosmic phenomenon known as the cosmic web, a vast network of galaxies, filaments, and voids that make up the structure of the universe. However, unlike most structures in the cosmic web, which tend to be more randomly distributed, the Sloan Great Wall forms a coherent, linear filament of galaxies stretching over 1.3 billion light-years. This makes the wall an anomaly, one that does not fit neatly into current models of galaxy formation. The general process of galaxy formation involves the gradual accumulation of matter under the influence of gravity. In the early universe, matter was distributed fairly evenly, with only slight fluctuations in density. These fluctuations eventually grew over time, with dark matter playing a key role in clumping matter together. This process led to the formation of galaxies, which were then pulled together by gravity to form clusters, superclusters, and eventually the large-scale filaments and walls of the cosmic web. In most cases, these structures are thought to have formed through a process of gravitational collapse. As matter accumulated in certain regions of space, it began to clump together, forming galaxies and galaxy clusters. Over billions of years, these clusters grew in size and number, eventually connecting to form long, thread-like filaments that make up the cosmic web. However, the Sloan Great Wall's shape and structure suggest that its formation may have involved additional, more complex factors. One possibility is that the Sloan Great Wall is the result of a cosmic flow, a large-scale motion of matter across the universe. During the early stages of the universe's evolution, regions of higher density may have acted like cosmic attractors, pulling surrounding matter toward them. This could have caused the galaxies that make up the Sloan Great Wall to align in a linear pattern, creating a structure that is not random, but instead shaped by the gravitational influence of large-scale cosmic flows. Recent computational models have begun to explore another intriguing possibility, that the Sloan Great Wall's formation may have been influenced by baryon acoustic oscillations, pressure waves that rippled through the early universe shortly after the Big Bang. These oscillations, frozen into the fabric of space as the universe cooled, could have created preferential zones where matter accumulated more readily. If the Sloan Great Wall formed along one of these ancient acoustic peaks, it would explain not only its immense length, but also its surprising coherence across such vast distances. This theory gained support from detailed analyses of the cosmic microwave background, which reveal patterns consistent with such large-scale imprinting. Furthermore, the wall's formation timeline remains a subject of intense debate. Did it assemble gradually over billions of years, with galaxies slowly migrating into position? Or did it form relatively quickly in the universe's youth, when matter was denser and gravitational interactions more frequent? Evidence from galaxy age distributions within the wall suggests a mixed scenario. Some regions appear ancient, while others show signs of more recent assembly, hinting at a complex, multi-stage formation process that challenges simple, linear models of structure growth. Another theory involves cosmic filaments. These massive, thread-like structures are believed to be the largest and most stable formations in the universe, acting as highways for the flow of matter. Galaxies tend to form along these filaments, creating long chains of galaxies that are bound together by gravity. The Sloan Great Wall may be one of these cosmic filaments, formed over billions of years as galaxies were drawn together by the gravitational pull of dark matter and surrounding clusters. This filament would be the result of the same forces that shape other cosmic structures, but its size and distinct linearity set it apart as something unique. However, the true cause of the Sloan Great Wall's unusual shape may never be fully understood. It's possible that its formation was influenced by factors we have yet to uncover, such as unknown aspects of dark energy or other cosmic forces. While current models provide a solid foundation for understanding how the wall fits into the larger cosmic structure, many of the details remain a mystery. What we do know is that the Sloan Great Wall exists within a universe that is constantly evolving. The forces of gravity, dark matter, and dark energy all contribute to the formation and shaping of structures like the wall, but the exact details of how and why it formed remain open questions. These questions highlight the limits of our current understanding of the universe and remind us that the cosmos is far more complex and dynamic than we can yet comprehend. One of the most important aspects of studying the Sloan Great Wall is that it challenges current models of cosmic evolution. The wall's size and linearity suggest that our understanding of large-scale structure formation is incomplete. It also raises important questions about the role of dark matter and dark energy in shaping the universe. While we have made significant strides in understanding these forces, the exact nature of their influence on structures like the Sloan Great Wall is still not fully understood. The study of the Sloan Great Wall is an ongoing process, and as technology advances, new discoveries may shed light on its formation. With upcoming missions like the James Webb Space Telescope, astronomers will be able to study the universe in even greater detail, potentially uncovering new insights into the origins of structures like the Sloan Great Wall. By continuing to map the cosmos and refine our understanding of cosmic forces, scientists hope to unravel the mystery behind the formation of this massive, enigmatic structure. The Sloan Great Wall is not just a fascinating feature of the universe, it is a window into the larger processes that shape the cosmos. Its formation, size, and structure present challenges to our current understanding of the universe and push the boundaries of what we know about galaxy formation, dark matter, and the cosmic web. As we continue to study the wall, we may uncover new truths about the universe's evolution and the forces that govern its structure. The role of dark energy in the formation of large-scale structures. As we continue to explore the Sloan Great Wall and its significance in the cosmic structure, it is important to consider the role of dark energy, one of the most enigmatic forces in the universe. While we've discussed the influence of dark matter in shaping large-scale structures like the Sloan Great Wall, dark energy plays an equally crucial, though very different, role in the universe's evolution. Dark energy is thought to make up approximately 68% of the total energy content of the universe, but its exact nature remains one of the biggest mysteries in cosmology. Unlike dark matter, which has mass and exerts gravitational pull, dark energy is a form of energy that appears to drive the accelerated expansion of the universe. It is this force that causes galaxies to move away from each other at an ever-increasing rate, an observation first made in the late 1990s through studies of supernovae and galaxy redshifts. While dark matter's gravitational influence is responsible for the formation of structures like the Sloan Great Wall, dark energy has the opposite effect. Rather than pulling matter together, dark energy pushes galaxies apart, increasing the rate of expansion of the universe. This interplay between the gravitational pull of dark matter and the repulsive force of dark energy creates a delicate balance in the universe's large-scale structure. In the case of the Sloan Great Wall, its formation was likely influenced by the early distribution of dark matter in the universe. However, as the universe expanded and dark energy became more prominent, the growth of structures like the Sloan Great Wall may have slowed down, or at least been altered by the accelerating expansion. Understanding how dark energy affects the formation of large structures is a complex task, as it requires understanding the balance between gravitational attraction and the repulsive force of dark energy over vast cosmic distances. Dark energy likely influenced the evolution of the cosmic web, the vast network of galaxies, filaments, and voids that we see today. In the early stages of the universe, when dark matter was the dominant force, galaxies and clusters of galaxies were drawn together to form large-scale structures. As dark energy began to dominate in the more recent history of the universe, the rate at which these structures grew was slowed. The interaction between dark matter and dark energy has led to a universe that is largely structured, with galaxies and galaxy clusters connected by filaments of dark matter, but with large voids in between. The Sloan Great Wall is part of this larger structure, a result of the interplay between these two cosmic forces. One of the key questions in cosmology is how dark energy has influenced the development of large-scale structures like the Sloan Great Wall. We know that dark energy has caused the accelerated expansion of the universe, but it is still unclear how it has influenced the growth of structures like the wall. For example, has dark energy caused the Sloan Great Wall to stretch out over time, or has it simply slowed its growth? These are questions that astronomers and cosmologists are still working to answer. To study the influence of dark energy on the cosmic web, scientists use a variety of observational techniques. One of the most important tools for this is the cosmic microwave background radiation, CM-buoy, the faint glow of radiation left over from the Big Bang. By studying the CMB, astronomers can learn about the early universe and how dark energy may have influenced its expansion. Additionally, the study of supernovae and galaxy redshifts provides important clues about the rate of expansion of the universe and how dark energy has accelerated this process over time. The relationship between dark energy and the Sloan Great Wall becomes even more intriguing when we consider the concept of the cosmic coincidence problem. This refers to the puzzling observation that dark energy's influence became dominant relatively recently in cosmic history, roughly around the same epoch when structures like the Sloan Great Wall reached their peak formation. Some cosmologists wonder whether this timing is truly coincidental or whether it reveals a deeper connection between structure formation and dark energy's nature. If dark energy's strength has varied over time, as some alternative models suggest, this could have profound implications for understanding how and when structures like the Sloan Great Wall stopped growing. Additionally, recent observations have detected subtle anomalies in the expansion rate of the universe at different scales, a phenomenon that could be related to how dark energy interacts with dense structures. Within massive filaments like the Sloan Great Wall, local gravitational dynamics may create regions where dark energy's effects are temporarily suppressed or enhanced. These variations, though small, could accumulate over billions of years to produce observable differences in structure formation patterns. Understanding these localized effects requires sophisticated models that account for both the quantum properties of dark energy and the classical gravitational dynamics of galaxy clusters, a challenge that pushes theoretical physics to its limits. The influence of dark energy is not limited to large-scale structures like the Sloan Great Wall. It affects every aspect of the universe's expansion, from the movement of individual galaxies to the evolution of the universe as a whole. Understanding how dark energy works is crucial for understanding the future of the universe. Will dark energy continue to accelerate the expansion of the universe indefinitely, or will its influence eventually wane? These are questions that scientists are working to answer, and the discovery of the Sloan Great Wall has added another layer of complexity to our understanding of dark energy's role in the universe. The future study of dark energy will likely involve larger-scale surveys and more powerful telescopes. The James Webb Space Telescope, set to launch soon, will provide new insights into the nature of dark energy by allowing astronomers to study distant galaxies and supernovae with unprecedented detail. This will help us understand how dark energy influences galaxy formation and large-scale structures like the Sloan Great Wall. As technology improves, we will continue to refine our understanding of dark energy and its impact on the universe's evolution. The Sloan Great Wall serves as a reminder that the universe is far more complex than we once thought. While dark matter and gravity have shaped the large-scale structures of the universe, dark energy has influenced the expansion and evolution of these structures. The interaction between these forces is still not fully understood, and the discovery of structures like the Sloan Great Wall continues to challenge our assumptions about how the universe works. As we continue to explore these cosmic forces, we will gain a deeper understanding of the forces that shape the universe and our place within it. The role of galaxies within the Sloan Great Wall. One of the most fascinating aspects of the Sloan Great Wall is how galaxies within it interact and evolve. While we typically think of galaxies as isolated objects moving through the void of space, the Sloan Great Wall reveals a far more intricate network of interactions. These galaxies, which make up the wall's structure, are not just passive entities, but active participants in the formation of this colossal feature of the universe. The galaxies within the Sloan Great Wall are part of a large-scale gravitational structure that has been shaped by the forces of dark matter and gravity over billions of years. The galaxies in the wall are not scattered randomly. Instead, they are arranged in a way that forms a coherent filament stretching across 1.3 billion light-years. This alignment is not just a random occurrence, but is the result of cosmic forces pulling the galaxies into place over a long period. One of the most interesting things about the galaxies in the Sloan Great Wall is their movement. Like all galaxies, the galaxies within the wall are in motion, but their movements are not random. The gravitational pull of the dark matter that binds the wall together influences the motion of these galaxies, causing them to move toward one another. This gravitational interaction has led to the formation of dense regions of galaxies, which we refer to as galaxy clusters. These clusters, which sit at various points along the Sloan Great Wall, are connected by threads of galaxies, creating a continuous filament of matter stretching across the cosmos. The interaction between galaxies within the Sloan Great Wall has a profound impact on their evolution. As galaxies move toward each other and collide, they can merge to form even larger galaxies. These collisions are not just violent events, but are also essential for the evolution of galaxies. When galaxies collide, they exchange gas and stars, leading to the formation of new stars and the growth of the galaxy. This process of galaxy merging is thought to be a fundamental part of how galaxies evolve over time. In addition to merging, galaxies within the Sloan Great Wall can also experience gravitational lensing. This phenomenon occurs when the gravitational field of a massive galaxy or galaxy cluster bends the path of light coming from galaxies behind it. This effect can magnify and distort the light from distant galaxies, allowing astronomers to study galaxies that would otherwise be too faint or too far away to detect. Gravitational lensing has proven to be an invaluable tool for studying the universe and has helped astronomers understand the distribution of dark matter and the formation of large-scale structures like the Sloan Great Wall. The chemical evolution of galaxies within the Sloan Great Wall also tells a compelling story. Spectroscopic studies reveal that galaxies in the densest regions of the wall tend to have different metallicity profiles compared to those in less dense areas or in the voids. This suggests that the wall's environment has influenced not just the physical arrangement of galaxies, but also their internal evolution. Galaxies in close proximity experience enhanced rates of tidal interactions, which can strip away gas and trigger intense bursts of star formation. This environmental processing means that a galaxy's location within the wall, whether in a dense cluster node or along a thinner filament strand, can fundamentally alter its evolutionary trajectory over cosmic time. Moreover, observations indicate that the Sloan Great Wall may serve as a conduit for intergalactic gas flows. Cold gas streams threaded along the dark matter filaments can fuel star formation in galaxies positioned along the wall's length. These cosmic rivers of hydrogen and helium, invisible to optical telescopes, but detectable through radio observations and absorption line studies, represent a crucial but often overlooked component of the wall's ecosystem. The ongoing accretion of this fresh material helps sustain star formation in wall galaxies, potentially extending their active lifetimes compared to galaxies in more isolated environments. This dynamic picture transforms our view of the wall from a static structure into a living, evolving system. Another important feature of the galaxies within the Sloan Great Wall is their composition. The galaxies in the wall vary in size, shape, and type. Some are massive elliptical galaxies, while others are smaller, irregularly shaped galaxies. The diversity of these galaxies provides important clues about the evolution of the universe and the processes that govern galaxy formation. The interaction between these different types of galaxies within the wall may have contributed to the unique structure of the Sloan Great Wall. Despite the interaction between galaxies, the Sloan Great Wall is also home to galactic voids. These voids are regions within the wall where very few galaxies are present. While the wall itself is dense with galaxies, the voids between the filaments of galaxies are vast, almost empty regions of space. These voids are important because they provide insight into the overall distribution of matter in the universe. The presence of these voids suggests that the universe is not filled with a uniform distribution of galaxies, but instead it is structured in a way that forms galactic filaments and vast empty spaces. The galaxies within the Sloan Great Wall are not isolated from the rest of the universe. They are part of a larger network of galaxies that extends across the universe. While the Sloan Great Wall is one of the largest and most prominent structures in the universe, it is part of a greater web of galaxies, known as the cosmic web. which connects galaxies across vast distances. The structure of the Sloan Great Wall is a clear example of how gravitational forces shape the distribution of galaxies and the large-scale structure of the universe. Studying the galaxies within the Sloan Great Wall gives us valuable insights into the fundamental processes that govern the universe. By examining the motion, composition, and interactions of these galaxies, astronomers can gain a better understanding of how galaxies form, evolve, and interact. The Sloan Great Wall serves as an excellent laboratory for studying the large-scale structure of the universe and the forces that shape it. In the future, as astronomers continue to map the universe and gather more data, they will likely uncover even more details about the galaxies within the Sloan Great Wall. New technologies, such as the James Webb Space Telescope, will provide unprecedented views of distant galaxies and offer deeper insights into the processes that shape large-scale structures like the Sloan Great Wall. As we continue to study these cosmic features, we will not only learn more about the history of the universe, but also gain a better understanding of our place within it. The impact of the Sloan Great Wall on our understanding of cosmic evolution. The discovery of the Sloan Great Wall significantly shifted our understanding of how large-scale structures form in the universe. Prior to its discovery, astronomers had generally accepted that the universe was made up of a more evenly distributed arrangement of galaxies. However, the Sloan Great Wall challenges this notion, presenting itself as a vast, linear structure that appears to defy the natural spread of galaxies in space. Its discovery has led to new questions about the processes that govern the evolution of galaxies and the way invisible forces shape the universe's structure. One of the most important implications of the Sloan Great Wall's discovery is the reconsideration of how cosmic expansion affects the distribution of galaxies. The current model of the universe suggests that galaxies are not uniformly spread across space, but are instead grouped in large clusters and superclusters. These groupings form the strands of the cosmic web, with filaments connecting them and vast voids between them. The Sloan Great Wall is one of the largest and most prominent of these filaments, spanning 1.3 billion light-years. Its existence forces us to rethink how galaxies come together and how the overall structure of the universe develops over time. The cosmic web, a network of filaments and voids, was long thought to be shaped solely by the gravitational attraction of dark matter. The Sloan Great Wall, however, suggests that there may be additional forces at work in the large-scale structure of the universe. While dark matter certainly plays a major role in the formation of galaxies and clusters, the precise way in which these structures organize themselves remains a mystery. The Sloan Great Wall challenges the assumption that galaxies and large structures should form in a random, more evenly distributed manner. A key feature of the Sloan Great Wall is its scale. At 1.3 billion light-years long, it is one of the largest known cosmic structures. Yet its formation is still not fully understood. The fact that such a vast wall of galaxies could exist in the way it does suggests that there may be unknown aspects of cosmic evolution that we have yet to uncover. The discovery of this immense structure calls into question the established theories of how large-scale cosmic structures form. Are there forces at work that we don't fully understand? And if so, what are they? The Sloan Great Wall's massive size also brings into focus the role of dark energy in shaping the universe. Dark energy is the mysterious force responsible for the accelerated expansion of the universe. While its effects are most noticeable on the largest cosmic scales, dark energy may have played a role in shaping the size and alignment of structures like the Sloan Great Wall. Some theories suggest that dark energy could be causing the universe to expand at a faster rate, which may influence the formation and structure of galaxies and galaxy clusters. If this is true, it would have profound implications for our understanding of the universe's evolution. Another significant impact of the Sloan Great Wall on our understanding of cosmic evolution is the role of galaxy mergers. The Sloan Great Wall is not a simple grouping of galaxies. It is a highly structured and coherent arrangement of galaxies connected by darker matter filaments. This suggests that the galaxies within the wall have been influenced by each other through gravitational interactions, likely leading to galactic mergers. These mergers are an essential part of galaxy evolution and are thought to play a key role in the growth and transformation of galaxies. As galaxies within the Sloan Great Wall merge and interact, they could trigger the formation of new stars and even lead to the formation of new types of galaxies. One of the challenges in studying the Sloan Great Wall is the sheer size and complexity of the structure. While we know that it stretches across 1.3 billion light-years, we still have a limited understanding of its full extent. New observational technologies, such as the James Webb Space Telescope and future sky surveys, will help to provide more detailed information about the wall and its place in the cosmic web. By studying the Sloan Great Wall in greater detail, astronomers can begin to unravel the mysteries of its formation and better understand the processes that have shaped its structure over billions of years. The Sloan Great Wall is not just an isolated cosmic structure, it is part of a larger cosmic context. While it is one of the most significant discoveries in recent years, it is only one piece of a much larger puzzle. The discovery of this massive wall has sparked renewed interest in the study of large-scale cosmic structures, and it has forced astronomers to reconsider many of their assumptions about the universe's development. As our observational tools improve, we will be able to study the Sloan Great Wall and similar structures in more detail, providing new insights into the forces that shape the universe. In conclusion, the Sloan Great Wall has had a profound impact on our understanding of cosmic evolution. It challenges our assumptions about how galaxies and large-scale structures form and evolve, and it raises new questions about the role of dark energy, dark matter, and galaxy mergers in shaping the universe. As we continue to explore the cosmos, the study of structures like the Sloan Great Wall will be critical for advancing our understanding of the universe's history and its future. The future of cosmic mapping. As we look to the future of astronomical exploration, it's clear that our understanding of large-scale structures like the Sloan Great Wall is just beginning. Advances in technology and new observational methods will soon allow astronomers to map the universe in unprecedented detail, providing a clearer picture of how massive structures like the Sloan Great Wall fit into the larger cosmic framework. One of the most exciting tools in this future exploration is the James Webb Space Telescope, JWST, set to launch in the coming years. This powerful observatory will allow us to observe distant galaxies and large-scale structures with incredible precision, unveiling details about the universe's evolution that were previously impossible to discern. JWST's ability to study galaxies and cosmic structures across a wide range of wavelengths, from infrared to visible light, will open up new avenues for investigating how galaxies interact and form large-scale structures like the Sloan Great Wall. But even before the launch of JWST, astronomers have already begun using existing technologies to further refine our understanding of cosmic structures. Instruments like the Square Kilometre Array, SKA, an upcoming radio telescope will provide a detailed survey of the radio sky, helping scientists map the distribution of galaxies and uncover new structures in the universe. SKA's sensitivity will allow astronomers to study galaxy clusters, dark matter, and the role of cosmic filaments, offering insights into the forces that shape structures like the Sloan Great Wall. Additionally, ongoing projects like the Dark Energy Survey and the PAN-STARRS, Panoramic Survey Telescope and Rapid Response System, are already producing vast amounts of data, helping to refine our understanding of dark energy and how it influences the formation of large-scale structures. These surveys are essential for mapping the universe's vast expanses and understanding the effects of dark energy on the universe's expansion. By studying the distribution of galaxies and how they interact with each other, scientists can better predict the future evolution of cosmic structures and understand their role in the larger universe. computer simulations will also continue to be a key part of our exploration of the cosmos. These models, which simulate the behavior of galaxies, dark matter, and dark energy over time, allow astronomers to predict how structures like the Sloan Great Wall might evolve. With increasingly sophisticated simulations, scientists can test different theories of cosmic formation, refine our understanding of large-scale structure formation, and gain a deeper understanding of the universe's fundamental forces. However, it's not just about new tools and technologies. The sheer volume of data being collected by surveys like the Sloan Digital Sky Survey, SDSS, and others will provide an ongoing challenge for astronomers. As more and more galaxies are catalogued, the need for advanced data analysis techniques will become even more crucial. With data from millions of galaxies, astronomers must be able to separate the signals from the noise and pinpoint the most important structures. This challenge is already being met with machine learning and artificial intelligence, which are increasingly used to analyze vast datasets and identify patterns that would be difficult or impossible for humans to detect. Looking ahead, the goal is not just to map out more structures like the Sloan Great Wall, but to understand the forces that created them. By studying how these structures evolve over time, astronomers hope to answer some of the universe's biggest questions. How did the universe form? What role does dark matter play in its evolution? And how will cosmic structures continue to grow and change over billions of years? As we continue to explore and map the universe, we are bound to uncover more surprises. The Sloan Great Wall is just one example of the unexpected wonders that await us. But it is a reminder that the universe is far more complex and dynamic than we once thought. New discoveries will continue to push the boundaries of our understanding and challenge the existing models of cosmic formation. One thing is certain: as we look deeper into the universe, we will continue to find structures and phenomena that defy our expectations. The study of these structures, from the Sloan Great Wall to other colossal cosmic filaments, will be central to our understanding of the universe and its evolution. And with each new discovery, we'll come one step closer to understanding our place in the cosmos. Here are the 4 expanded sections, with the new additions smoothly integrated. How the Sloan Great Wall challenges our understanding of cosmic clusters. The Sloan Great Wall has forced astronomers to re-evaluate how we think about galaxy clusters and superclusters. Traditionally, the large-scale structures in the universe, such as galaxy clusters, have been understood as regions where galaxies are bound together by gravity, forming dense, massive structures. These clusters are usually the focal points of the cosmic web and tend to be surrounded by vast voids. The Sloan Great Wall, however, is a galaxy filament, which is fundamentally different from a galaxy cluster. This distinction is significant, and its implications stretch beyond the structure itself, challenging our understanding of cosmic organization. Most large-scale cosmic structures, like the Virgo supercluster, which includes our Milky Way, are thought to be gravitationally bound clusters of galaxies. These clusters are typically isolated by vast cosmic voids. A galaxy cluster is dense and gravitationally stable, with galaxies bound together by their mutual gravity. The Sloan Great Wall, in contrast, is a long, thin filament made up of galaxies arranged in a near-linear pattern with no central gravitational focus like a typical cluster. This distinction raises several important questions about the nature of large-scale cosmic structures. Can filaments like the Sloan Great Wall be considered superclusters, even though they don't fit the traditional definition? And if so, how do these filaments maintain their coherence and linearity across such vast distances? These are questions that challenge astronomers to think differently about how galaxy clusters and filaments are formed and how they interact. The formation of structures like the Sloan Great Wall is intricately tied to the distribution of dark matter. As mentioned in previous chapters, dark matter exerts a gravitational influence on galaxies, which leads to the formation of large-scale structures like the cosmic web. However, while galaxy clusters form around concentrations of dark matter, filaments like the Sloan Great Wall may have formed through a combination of dark matter and cosmic flows. The idea that large-scale cosmic filaments can form without a central gravitational pull, as is the case with the Sloan Great Wall, has forced astronomers to reconsider how dark matter and gravity function on the larger scales. What sets the Sloan Great Wall apart from traditional galaxy clusters is the lack of a dominant central mass. In a galaxy cluster, the gravitational pull from the central mass of galaxies creates a dense, gravitationally bound region. In the case of the Sloan Great Wall, however, the galaxies are connected by vast filaments of dark matter, and there is no central point of concentration. Instead, the mass is distributed more evenly across the structure, creating a giant web of galaxies and dark matter that stretches across billions of light years. This distributed architecture suggests that the wall's stability derives not from a single gravitational anchor, but from a continuous network of interconnected dark matter threads that maintain the structure's integrity across cosmic distances. Recent studies using weak gravitational lensing have revealed that these dark matter filaments display surprising uniformity in density, challenging models that predicted more irregular distributions. Another factor that complicates our understanding of the Sloan Great Wall is its unusual alignment. Unlike typical galaxy clusters, which are scattered more randomly across the universe, the galaxies in the Sloan Great Wall are aligned in a near-linear formation. The precise mechanism that caused this alignment remains a mystery. Some researchers suggest that it could be due to large-scale cosmic flows that have caused galaxies to move in a certain direction, but this remains speculative. Regardless of the exact cause, the linearity of the Sloan Great Wall presents a new challenge for our models of how galaxies and large-scale structures are arranged in the universe. The interactions between galaxies within the Sloan Great Wall also differ from those in typical galaxy clusters. In a galaxy cluster, galaxies interact through gravitational attraction and often undergo galactic mergers, where two or more galaxies collide and merge into a single, larger galaxy. This process can lead to the creation of massive elliptical galaxies. In the Sloan Great Wall, however, galaxies are more evenly distributed across the filament, and their interactions are less chaotic. While some mergers still occur, the galaxies within the wall are generally not as tightly bound to each other as those in a traditional cluster. Instead, the galaxies are connected through gravitational filaments, where dark matter plays a major role in linking them together. The relative velocities of galaxies within the wall tend to be lower than those in dense cluster cores, resulting in fewer high-speed collisions and a different evolutionary pathway. This gentler dynamic environment may preserve certain galactic features, such as spiral structures and gas reservoirs, that are typically disrupted in the violent cores of massive clusters. This difference in galaxy interaction raises another question. Could the Sloan Great Wall represent a different mode of galaxy formation than what we typically see in galaxy clusters? Is it possible that filaments like the Sloan Great Wall are a transitional stage in the formation of galaxy clusters? As galaxies continue to move toward one another, could the Sloan Great Wall eventually collapse into a massive, gravitationally bound cluster? Or will the galaxies in the wall continue to spread out, forming more independent structures over time? These questions underscore the complexity of large-scale cosmic structure and the need for new models to explain the formation and evolution of structures like the Sloan Great Wall. While much progress has been made in understanding the role of dark matter and dark energy in shaping these structures, the Sloan Great Wall remains an anomaly that forces scientists to revisit their assumptions about how galaxies are distributed and how they evolve. The discovery of the Sloan Great Wall also highlights the importance of ongoing surveys and observations. With current technologies, we are only scratching the surface of understanding the full extent of large-scale cosmic structures. As future telescopes and surveys provide more detailed observations, it is likely that astronomers will uncover even more structures like the Sloan Great Wall, leading to further revisions of our models of the universe. In conclusion, the Sloan Great Wall challenges our understanding of cosmic structure by presenting an example of a large-scale filament that defies traditional models of galaxy clusters. The lack of a central gravitational focus, the unusual alignment of galaxies, and the role of dark matter and dark energy all contribute to the uniqueness of the structure. The study of the Sloan Great Wall is an ongoing process, and as we continue to explore the cosmos, new discoveries will shed light on the formation and evolution of this colossal feature in the universe. The influence of the Sloan Great Wall on the local universe. The discovery of the Sloan Great Wall has had a profound effect not only on our understanding of the universe, but also on how we view our place in the cosmos. As one of the largest known structures in the observable universe, it challenges the traditional view that galaxies are evenly distributed across space. Instead, the Sloan Great Wall represents a massive, interconnected chain of galaxies that spans across 1.3 billion light-years. Its existence forces us to re-evaluate the assumptions we've made about the local universe, the vast but still limited section of space that we can observe directly. The Sloan Great Wall resides in a relatively local region of the universe, meaning it is relatively close to our own Milky Way galaxy, at least by cosmic standards. It is part of a larger network of galaxy filaments, clusters, and superclusters that stretch across the universe, forming what is known as the cosmic web. While the Sloan Great Wall is one of the most prominent and well-defined features of the cosmic web, it is far from the only one. The entire universe is filled with vast networks of galaxies, each connected by invisible threads of dark matter, the gravitational glue that holds these massive structures together. One of the most significant impacts of the Sloan Great Wall is that it has shifted our perspective of galactic distribution. Before its discovery, many astronomers believed that galaxies were mostly scattered randomly throughout the universe, with some areas being more densely populated than others. However, the Sloan Great Wall's size and linearity suggest a much more organized structure at a grander scale. The alignment of galaxies within the wall is not the result of random chance, but rather a product of cosmic forces, primarily gravity and dark matter, acting over billions of years. This discovery has led to new questions about the role of dark matter in shaping the universe. Dark matter, which makes up a significant portion of the mass of the universe, does not interact with light or other forms of electromagnetic radiation. Despite this, it exerts a strong gravitational pull, influencing the motion and distribution of galaxies. The fact that the Sloan Great Wall is composed of galaxies bound together by dark matter suggests that these invisible forces play a crucial role in shaping the large-scale structure of the universe. The wall itself may be one of the largest and most well-defined examples of this phenomenon, where dark matter's influence is most clearly visible. Detailed kinematic studies of galaxies within the wall have revealed coherent, large-scale motions that align with theoretical predictions of dark matter flow patterns, providing some of the strongest observational evidence for dark matter's role in structuring the cosmos. Another important consideration is the effect of the Sloan Great Wall on the local universe's evolution. The formation of the Great Wall likely influenced the motion and growth of galaxies within the local group of galaxies, which includes the Milky Way. The gravitational forces exerted by the Sloan Great Wall could have affected the movement of galaxies within this region, possibly altering their orbits and interactions. Some researchers have speculated that the large-scale structures in the local universe, including the Sloan Great Wall, may have played a role in the formation of galaxy clusters like the Virgo cluster, which is home to the Milky Way, and over 1,000 other galaxies. The wall's gravitational influence may extend hundreds of millions of light-years, creating subtle perturbations in the velocities of nearby galaxy groups that accumulate over cosmic time. These gravitational ripples could have guided the early assembly of our local supercluster, effectively channeling matter along preferred pathways that ultimately determined where dense structures would emerge. The existence of the Sloan Great Wall also raises important questions about galactic mergers and their role in shaping the universe. As galaxies within the wall move toward each other under the influence of dark matter and gravity, they are likely to collide and merge. These mergers are an essential part of the galaxy formation process, contributing to the growth of larger galaxies over time. In fact, the Milky Way itself is believed to have been formed through a series of mergers with smaller galaxies over billions of years. The Sloan Great Wall, with its immense scale and linearity, presents a unique environment for studying how galaxy mergers affect the evolution of the universe. Interestingly, the presence of the Sloan Great Wall also brings attention to the importance of voids in the local universe. The voids between the filaments of galaxies are just as important as the filaments themselves. These vast empty spaces help define the structure of the cosmic web and play a significant role in how galaxies move and interact. The presence of the Sloan Great Wall suggests that the universe is not just a random distribution of matter, but a highly organized structure with distinct regions of dense galaxies and vast, empty voids. The interplay between these dense filaments and the voids between them is a key factor in shaping the universe's evolution. The local universe, which includes everything within a few billion light years of Earth, is just one part of the cosmic web. Beyond our region lies an even more vast and complex network of galaxies, clusters, and filaments. As astronomers continue to map the universe and observe larger structures, they will be able to study how the Sloan Great Wall fits into the broader structure of the cosmos. The Sloan Great Wall is just one example of how large-scale structures can shape the evolution of galaxies, and understanding how it interacts with other structures will be critical for understanding the overall evolution of the universe. The cosmic web represents the universe's largest structures, but it is also a reminder of the fragility and scale of our place in the cosmos. The fact that the Sloan Great Wall exists in such close proximity to us, in cosmic terms, serves as a powerful reminder that we are just one part of an immense and dynamic universe. While the Sloan Great Wall is an impressive structure, it is also just one of many in the universe's vast network of galaxies and filaments. As technology continues to improve, future discoveries will shed more light on the true nature of the cosmic web and the role that structures like the Sloan Great Wall play in the evolution of the universe. In the end, the study of the Sloan Great Wall serves as a powerful reminder of how much we still have to learn about the universe. With each new discovery, we come closer to understanding how these massive structures form, how they evolve, and how they fit into the grand picture of the cosmos. And with the continued advancement of observational technology, the answers to these questions are sure to come, bringing us closer to understanding the universe and our place within it. The connection between the Sloan Great Wall and other galactic structures. The Sloan Great Wall is one of the most intriguing structures in the universe, but it is by no means isolated. In fact, it is just one part of a vast interconnected network of galaxies, clusters, and voids that make up the cosmic web. Understanding how the Sloan Great Wall relates to other large-scale structures in the universe can provide deeper insights into how galaxies are distributed, how they evolve, and how the universe as a whole functions. One of the first things to note is that the Sloan Great Wall is not the only wall-like structure in the universe. There are other similar, large-scale filaments of galaxies scattered across the cosmos. These structures are connected by a web of dark matter, which acts as the gravitational glue holding galaxies together. The presence of multiple large filaments suggests that the cosmic web is a fundamental feature of the universe's structure. The Sloan Great Wall, with its 1.3 billion light-year length, is one of the most well-known and best-studied examples of these cosmic filaments, but it is far from unique. The Laniakea supercluster, for instance, is a massive collection of galaxies that includes the Milky Way and spans across 500 million light-years. The Sloan Great Wall, while much smaller in comparison, is a part of this larger structure, demonstrating the interconnectedness of galaxies on a cosmic scale. The supercluster contains many smaller filaments, including the Sloan Great Wall, and the gravitational forces that bind them together shape the overall structure of the universe. Another well-known structure related to the Sloan Great Wall is the Hercules Corona Borealis Great Wall, which was discovered in 2013. This enormous structure is even larger than the Sloan Great Wall and is considered the largest known superstructure in the universe. It stretches across 10 billion light-years, vastly surpassing the Sloan Great Wall in size. While the Sloan Great Wall is just one part of the cosmic web, the Hercules Corona Borealis, Great Wall is an extreme example of the kind of large-scale, interconnected structure that defines the universe's layout. Both of these structures, along with others like the Coma Cluster and Virgo Cluster, show the intricate connections between galaxies and the gravitational forces that tie them together. These large-scale structures form the backbone of the universe, providing the framework upon which galaxies, stars, and other cosmic entities are organized. While the Sloan Great Wall is one of the most prominent features, it is ultimately just a part of a greater system of galactic structures. Comparative studies between these megastructures have revealed fascinating patterns in their formation epochs and evolutionary trajectories. The Sloan Great Wall appears to have formed during a particularly active period of cosmic structure assembly, roughly 7 to 9 billion years ago, when the universe's expansion rate and dark matter distribution created ideal conditions for such massive filament formation. A critical factor in the connection between the Sloan Great Wall and other galactic structures is the role of dark matter. This mysterious substance makes up approximately 85% of the universe's mass, and its gravitational pull is essential in shaping large-scale structures. Dark matter doesn't interact with light, making it invisible to traditional telescopes. However, astronomers have been able to detect its presence through its gravitational effects on visible matter. The gravity of dark matter plays a key role in pulling galaxies together, allowing them to form clusters and filaments, like the Sloan Great Wall. Without dark matter, the cosmic web would not exist in the same way, and structures like the Sloan Great Wall would not be possible. Additionally, the discovery of the Sloan Great Wall has raised important questions about galaxy clustering and supercluster formation. Why do galaxies group together in such an organized way? How do these clusters and superclusters form? One of the leading theories is that cosmic flows, large-scale motions of matter in the universe, play a crucial role in the formation of galaxy filaments. These cosmic flows, caused by the gravitational pull of large structures like dark matter and galaxy clusters, help galaxies move toward one another, eventually forming larger structures like the Sloan Great Wall. In fact, some scientists believe that the formation of the Sloan Great Wall is the result of the cosmic flow of galaxies moving towards a region of higher density. This process of galaxy accumulation is known as cosmic attraction, and it is a key factor in the formation of structures like the Sloan Great Wall. The galaxies within the wall are not evenly distributed, but rather tend to cluster along the filaments. This clustering effect is influenced by dark matter, which provides the gravitational pull that drives the motion of galaxies within the cosmic web. Advanced velocity surveys have mapped these flows in unprecedented detail, revealing a complex hierarchy of motions where smaller streams feed into larger currents, ultimately converging at the densest nodes of the cosmic web, where structures like the Sloan Great Wall reside. As the study of large-scale structures like the Sloan Great Wall progresses, it will likely become clearer how these massive cosmic features relate to each other. Astronomers are working with more advanced tools and technologies to map the universe in greater detail. And as observational techniques improve, we may uncover even more structures that challenge our understanding of how galaxies are distributed and how the universe evolves. One key tool in this ongoing research is gravitational lensing. This phenomenon occurs when the gravity of a large structure, such as a galaxy cluster, bends and distorts the light from objects behind it. By studying the way light is bent, scientists can map the distribution of dark matter and uncover hidden structures in the universe. Gravitational lensing has already provided valuable information about the Sloan Great Wall and other large-scale structures, and it will continue to play a vital role in our understanding of the cosmic web. Another tool that will help us understand the connection between the Sloan Great Wall and other galactic structures is cosmological simulations. These computer-generated models simulate the evolution of the universe over billions of years, taking into account the effects of gravity, dark matter, dark energy, and other factors. These simulations have already provided valuable insights into the formation of the cosmic web, and they will continue to be an essential part of the research into large-scale structures like the Sloan Great Wall. As we continue to map the universe and explore its most distant corners, we will likely uncover more features like the Sloan Great Wall, massive structures that shape the universe's layout and provide insight into the forces that govern its evolution. Understanding how the Sloan Great Wall connects to other cosmic structures is essential for refining our models of the universe and gaining a deeper understanding of its underlying mechanics. The unseen force behind the wall. As we delve deeper into the formation of large-scale cosmic structures like the Sloan Great Wall, one crucial element continues to emerge as a dominant force: dark matter. While we cannot directly observe dark matter because it does not emit or interact with light, its presence is felt through its gravitational effects on visible matter. Dark matter is estimated to make up about 85% of the mass of the universe, yet its exact nature remains one of the greatest mysteries in modern astrophysics. Despite its invisibility, dark matter plays a central role in the formation of structures like the Sloan Great Wall, and understanding its properties is key to unlocking the secrets of the universe. Dark matter is not just a theoretical concept, but a real, measurable influence on the universe's large-scale structure. The discovery of the Sloan Great Wall and other massive structures has provided compelling evidence for the role of dark matter in shaping the cosmic web. The galaxies in the Sloan Great Wall, as well as those in other large-scale structures, are bound together by the gravitational pull of dark matter. Without dark matter, these filaments and clusters of galaxies would not exist in the same way. The fact that the Sloan Great Wall is so large and so well defined suggests that dark matter's influence is not only real, but also immense. One of the most compelling pieces of evidence for the existence of dark matter comes from gravitational lensing. As mentioned in previous chapters, gravitational lensing occurs when light from distant objects is bent and distorted by the gravity of a massive object, such as a galaxy cluster. This effect allows astronomers to map the distribution of dark matter by observing how it bends light. The Sloan Great Wall, with its vast network of galaxies and galaxy clusters, acts as a natural laboratory for studying the effects of dark matter. By studying how light is bent around these structures, astronomers can infer the distribution of dark matter within the wall and other large-scale features of the universe. Recent weak lensing surveys have produced three-dimensional maps of dark matter distribution along the wall's length, revealing a remarkably filamentary structure that closely matches theoretical predictions from cold dark matter models. While dark matter is responsible for the formation and structure of the Sloan Great Wall, it also plays a crucial role in the overall organization of the cosmic web. The cosmic web is composed of vast filaments of galaxies and galaxy clusters, separated by enormous voids. These filaments are not randomly distributed. Instead, they form a highly organized structure that is shaped by the gravitational forces of dark matter. Dark matter acts as the invisible scaffolding that holds these filaments together, pulling galaxies into long, interconnected strands that form the backbone of the cosmic web. The Sloan Great Wall, as one of the most prominent examples of this structure, offers a glimpse into the powerful role that dark matter plays in organizing the universe. The hierarchical nature of dark matter clustering, from small halos around individual galaxies to the massive filaments spanning billions of light years, demonstrates how gravitational amplification of primordial density fluctuations has sculpted the universe's architecture over cosmic time. However, despite its importance, dark matter remains elusive. Scientists have attempted to detect dark matter directly through experiments that search for its interactions with normal matter, but so far these efforts have been unsuccessful. The most widely accepted theory of dark matter is that it consists of weakly interacting massive particles, WIMPs, which are hypothetical particles that do not interact with light, but have mass and can influence the gravitational pull of objects. However, other theories propose that dark matter may be made of axions, sterile neutrinos, or other exotic particles. While we have yet to detect dark matter directly, its gravitational effects are undeniable, and its presence is felt in the way galaxies and structures like the Sloan Great Wall are distributed across the universe. The study of dark matter is not limited to just understanding large-scale cosmic structures like the Sloan Great Wall. Dark matter also plays a key role in the evolution of galaxies. The presence of dark matter in and around galaxies helps shape their structure and influences their motion. For example, in galaxy clusters, dark matter is thought to form a dark matter halo around each galaxy, which exerts a gravitational pull that helps to bind the galaxy together. Without this dark matter halo, galaxies would not have the gravitational stability necessary to maintain their shape. The study of dark matter's role in galaxy formation and evolution is an ongoing field of research, and new discoveries in this area may shed light on the way galaxies like those in the Sloan Great Wall formed. Another critical aspect of dark matter is its relationship to dark energy, the mysterious force responsible for the accelerated expansion of the universe. While dark matter pulls galaxies together, dark energy works in the opposite direction, pushing galaxies apart and accelerating the expansion of the universe. Together, these two forces play a central role in shaping the universe's large-scale structure. Understanding the interplay between dark matter and dark energy is crucial for understanding the future evolution of the universe and the way structures like the Sloan Great Wall will evolve over time. In the coming years, new observational tools and missions, such as the James Webb Space Telescope and the Large Synoptic Survey Telescope, ILSST, will help astronomers study dark matter in even greater detail. These instruments will provide more precise measurements of the distribution of dark matter in the cosmos, allowing scientists to better understand how it shapes the universe. By studying the Sloan Great Wall and other large-scale structures, astronomers will continue to refine their models of dark matter and its role in the evolution of the universe. The Sloan Great Wall, as one of the most massive structures in the observable universe, serves as a perfect example of the influence of dark matter on the cosmos. While the exact nature of dark matter remains unknown, its effects on the formation of the Sloan Great Wall and other cosmic structures are undeniable. The wall's existence challenges our understanding of the universe and pushes us to rethink our models of galaxy formation, large-scale structure, and the forces that shape the cosmos. As we continue to study dark matter, we will uncover more about the fundamental forces that govern the universe and our place within it. Gravitational waves and the impact on large-scale structures. The study of gravitational waves, ripples in space-time caused by massive objects accelerating through the universe, has opened up an entirely new field of astronomy, with significant implications for understanding large-scale structures like the Sloan Great Wall. While gravitational waves were first predicted by Albert Einstein in his theory of general relativity more than a century ago, it wasn't until recently that scientists were able to detect them directly. The first detection of gravitational waves in 2015 by the LIGO Laser Interferometer Gravitational Wave Observatory team marked a monumental step in our ability to study the universe on an entirely new scale. Gravitational waves are produced by violent events such as the merging of black holes, the collapse of massive stars, or the motion of large objects in space. These waves travel through space-time at the speed of light, causing slight distortions in the fabric of space and time. When detected, gravitational waves provide a unique way to observe the universe, offering information that is otherwise inaccessible through traditional means like light or electromagnetic radiation. The connection between gravitational waves and large-scale cosmic structures, including the Sloan Great Wall, comes from the fact that these waves can travel across the entire universe, interacting with structures on vast cosmic scales. While gravitational waves typically carry information about the objects and events that produce them, such as the collision of black holes, they also have the potential to reveal the properties and behaviours of the large-scale structures that exist between these events. In theory, gravitational waves could provide valuable insight into the dynamics of structures like the Sloan Great Wall. For example, large-scale cosmic filaments, such as the one that forms the Sloan Great Wall, are composed of galaxies, dark matter and gas, all of which exert gravitational forces on one another. While the influence of dark matter is already understood to play a role in the formation of such structures, gravitational waves could provide an entirely new layer of data. By studying how these waves interact with large-scale structures, astronomers may be able to observe how galaxies move and evolve within the cosmic web. Another potential connection between gravitational waves and the Sloan Great Wall lies in the detection of cosmic collisions. The merging of large galaxy clusters or the collision of supermassive black holes could generate gravitational waves that travel across the universe, providing crucial information about the nature of these events. These events could affect the structure of large-scale cosmic formations, like the Sloan Great Wall, potentially triggering the movement of galaxies or altering the distribution of matter across vast distances. Gravitational waves, therefore, could serve as a tool for directly observing the forces at work in the creation and evolution of these colossal structures. The Sloan Great Wall is just one example of how gravitational waves could enhance our understanding of the universe. By measuring and analysing gravitational waves that pass through these massive structures, scientists could gain new insights into the distribution of matter and the role of dark matter in shaping large-scale cosmic features. Moreover, gravitational waves could help us understand how the forces that govern the universe operate over cosmic time. Just as gravitational waves can reveal the most violent cosmic events, they may also offer us a unique perspective on the quieter processes that shape the large-scale structure of the universe. The LIGO and Virgo collaborations, which have been responsible for detecting gravitational waves, continue to work toward improving our ability to detect and analyse these waves. As these collaborations grow and evolve, they may enable scientists to study gravitational waves on an even larger scale, allowing for more detailed observations of how these waves interact with large-scale structures. Future space-based observatories such as the LISA, Laser Interferometer Space Antenna, mission will be crucial in expanding our ability to detect gravitational waves, especially in the low-frequency range, which will allow us to study different types of cosmic events and structures. While the primary focus of gravitational wave astronomy has been on detecting events like black hole mergers, the potential for studying large-scale structures like the Sloan Great Wall offers an exciting frontier for this field. As we continue to push the boundaries of gravitational wave detection, we will gain an increasingly detailed understanding of the universe and the forces that shape it. These discoveries will not only shed light on the mysteries of large-scale cosmic structures, but also help us understand the fundamental forces of nature on the grander scale. The detection of gravitational waves has already revolutionized the way we study the universe. As technology continues to advance, and as our understanding of gravitational wave astronomy deepens, the role of these waves in understanding the formation and evolution of structures like the Sloan Great Wall will become even more significant. With the development of new instruments and advanced techniques, astronomers are poised to uncover more information about how the universe's most massive structures were formed and how they continue to evolve. the significance of the Sloan Great Wall in cosmological models. The Sloan Great Wall stands as one of the most significant discoveries in the field of cosmology, not just because of its immense size, but due to its challenge to existing models of the universe. Its discovery forced astronomers to reconsider the framework used to understand large-scale cosmic structure. Up until the identification of such structures, cosmological models, particularly those related to the cosmic web and galaxy formation, often assumed that the universe's matter was distributed more uniformly. Before the Sloan Great Wall, cosmologists believed that large-scale structures in the universe, like galaxies and clusters, were formed in a relatively more dispersed manner. However, the wall's discovery shattered this uniformity by introducing a filament-like feature so vast that it appears to stretch the very fabric of space itself. The Sloan Great Wall challenges this classic model by showcasing the existence of vast cosmic filaments, revealing that the universe's structure is far more intricate and organized than initially understood. The cosmic web, once thought to be a simple pattern, is now recognized as a highly structured network of galaxy clusters, galactic filaments, and voids. The Sloan Great Wall offers a clear, visible example of this interconnected structure, where billions of galaxies are aligned in a filament, linked by dark matter, and stretching across 1.3 billion light-years. This alignment suggests that the universe's growth follows patterns shaped by gravitational forces and cosmic flows, which differ from the earlier, more simplistic models that suggested galaxies simply drifted through space. At the core of the discovery of the Sloan Great Wall is the realization that galaxies are not isolated. They are part of a grand design, the cosmic web, where they are bound together by the force of gravity and dark matter. The wall's enormous length and its connection with the surrounding cosmic web is a manifestation of the way galaxies are drawn together and how they form large, interconnected structures. While galaxy clusters, such as the Virgo cluster, have long been known, the discovery of the Sloan Great Wall opened the door to studying how entire filaments of galaxies and dark matter are connected in a way that was previously unimaginable. The significance of the Sloan Great Wall goes beyond the fact that it exists. It has become a benchmark in cosmology for understanding the large-scale structure of the universe. It has reshaped the cosmic web model, moving it from a conceptual theory to an observable phenomenon that exists on a scale far larger than any previously known cosmic feature. The wall is the largest known structure in the observable universe, and it presents a fascinating challenge to scientists who must now explain how such massive cosmic formations come into existence. While the Sloan Great Wall is a remarkable structure, its discovery also raises questions about how other large-scale structures form. If such a massive feature could emerge within the observable universe, what other similarly immense structures lie beyond our current observational limits? Astronomers are beginning to realize that the universe may be far more structured than previously believed. The fact that the Sloan Great Wall is not an isolated feature, but part of a network of large structures, suggests that the cosmic web may consist of even larger formations that have yet to be discovered. Understanding how these massive structures are created requires a deeper look into the gravitational forces at play. In the past, dark matter was thought to play a relatively minor role in the formation of large-scale structures. However, the Sloan Great Wall has shifted that view, showing that dark matter's influence is central to the formation of these filaments and walls. The invisible substance not only binds galaxies together, but also shapes the structure of the entire cosmic web. The way dark matter interacts with regular matter, i.e., the visible galaxies and gas, helps to create the kind of filamentary structure that is seen in the Sloan Great Wall. The evolution of these structures involves more than just dark matter. Gravitational forces between galaxies within the wall also play a critical role. In a sense, the Sloan Great Wall serves as a cosmic laboratory for studying how gravitational interactions between galaxies contribute to the formation of such large-scale structures. Galaxies are not static. They move, collide, and interact with each other over vast timescales, a process that continues to reshape the cosmic web. These interactions, coupled with the influence of dark matter, drive the evolution of the cosmic web and create the kinds of features seen in the Sloan Great Wall. As cosmologists continue to study the Sloan Great Wall and similar structures, they will refine their models of galaxy formation and cosmic evolution. The wall's size and alignment with dark matter filaments offer valuable insight into how large-scale structures evolve over time. For example, as galaxies continue to move and interact, the wall could grow, merge with other structures, or break apart due to the competing forces of gravity and cosmic expansion. The future of the Sloan Great Wall and similar cosmic filaments will be shaped by the ongoing study of cosmic flows and the forces that govern them. The implications of the Sloan Great Wall are also significant for the study of cosmological evolution. Its discovery forces us to reconsider how galaxies have evolved over billions of years. Could the wall represent the final stage in the formation of a supercluster, or is it merely one phase in the continuous evolution of the cosmic web? Understanding how these massive structures form and evolve is essential for refining cosmological models and predicting the future of the universe. As new observational tools and simulation techniques become available, scientists will continue to study the Sloan Great Wall and other large-scale structures in greater detail. The future of cosmology lies in understanding these grand structures and the forces that shape them. The Sloan Great Wall has provided a glimpse into the universe's grand design. But as technology and theory evolve, more discoveries are sure to follow, deepening our understanding of the universe's largest and most mysterious structures. In conclusion, the Sloan Great Wall has significantly altered our view of the universe. It is no longer just an isolated feature in the cosmic web. It has become a critical piece in the puzzle of cosmic structure formation. Its sheer size, shape, and gravitational behavior challenge existing cosmological models, forcing us to rethink how the universe's largest features are organized and how they evolve over time. As we continue to study these massive cosmic structures, we will uncover new insights into the universe's evolution and our place within it. The Sloan Great Wall and the expanding universe. The Sloan Great Wall not only reshapes our understanding of galactic structures, but also plays a significant role in how we think about the expanding universe. The discovery of such a vast and complex structure challenges existing models of cosmic expansion, which have traditionally been based on the assumption that large-scale cosmic structures are formed through random processes over time. The wall's size, symmetry, and the sheer scale of its influence on nearby galaxies suggest that the expansion of the universe is not as straightforward as we believed. Instead, the Sloan Great Wall may offer a glimpse into the deeper mechanics of cosmic expansion and how it interacts with large-scale structures. The Big Bang Theory, which remains the dominant model for understanding the universe's origin, describes the universe as expanding from a hot, dense state into the vast cosmos we observe today. This expansion is happening in all directions, and as the universe expands, galaxies move away from each other. However, the discovery of structures like the Sloan Great Wall raises important questions about the consistency of this expansion on very large scales. Unlike the more random distribution of galaxies expected in a uniformly expanding universe, the Sloan Great Wall represents a highly organized structure of galaxies and dark matter. It appears that rather than galaxies being distributed uniformly across space, there are vast regions where they are tightly concentrated and others where they are virtually absent. This observation forces scientists to reconsider how cosmic expansion works on large scales. Could it be that the expansion of the universe is not just a simple, even process, but rather one that is influenced by the gravitational forces within the cosmic web? The Sloan Great Wall, with its vast size and complex structure, suggests that large structures can act as anchor points within the expanding universe. These structures could be the result of local gravitational collapses, where regions of space have collapsed under their own gravity to form large, dense structures. This would imply that while the universe is expanding overall, local gravitational forces may still dominate the behavior of galaxies and cosmic structures in certain regions. One of the key aspects of the Sloan Great Wall's formation is the role of dark matter and dark energy. Dark matter is the invisible substance that exerts gravitational pull on galaxies and clusters of galaxies, while dark energy is thought to be responsible for the accelerated expansion of the universe. The interplay between these two forces is key to understanding the formation and evolution of structures like the Sloan Great Wall. Dark matter pulls galaxies together to form large structures, while dark energy works in the opposite direction, causing the universe to expand more rapidly over time. The presence of these opposing forces means that the Sloan Great Wall could be an example of how these forces work together to shape the universe's large-scale structure. Additionally, the expanding universe could be influencing how the galaxies within the Sloan Great Wall move relative to each other. If galaxies in the wall are moving away from each other due to cosmic expansion, the sheer size of the wall could provide clues about the speed and scale of this expansion. The fact that the wall spans 1.3 billion light-years in length suggests that the forces responsible for the wall's formation may have been at work for billions of years, shaping the wall even as the universe itself continues to expand. The interactions between galaxies and dark matter in the Sloan Great Wall may offer a more nuanced understanding of how the expansion of the universe is affecting the largest cosmic structures. One critical feature of the Sloan Great Wall is its relationship to other large cosmic structures, like the Hercules Corona Borealis Great Wall. The sheer size of these cosmic formations suggests a more complex and interwoven structure of the universe, one where regions of high density and vast cosmic voids coexist and interact. The discovery of these structures is a direct challenge to the earlier model of the universe as a more uniform and isotropic space. Rather than expanding uniformly, the universe seems to contain vast regions where gravitational forces have pulled galaxies together, creating structures that can persist across vast distances. This realization is fundamental in understanding not only the Sloan Great Wall, but also the future of large-scale structures. To further understand the impact of the expanding universe on the Sloan Great Wall, we must also consider the role of cosmic inflation. This theory posits that in the moments following the Big Bang, the universe expanded at an exponentially rapid rate, smoothing out irregularities and shaping the distribution of matter we see today. Cosmic inflation could explain the uniformity of the universe on large scales, while also allowing for the formation of dense structures like the Sloan Great Wall. As the universe continued to expand after the inflationary period, these irregularities, or pocket regions of more concentrated matter, would have eventually coalesced into the massive structures that we observe today. The Sloan Great Wall is one of the clearest examples of this process, offering insight into how the universe's expansion could have influenced the formation of large-scale structures. In the context of the Sloan Great Wall, the expanding universe is not simply a backdrop for cosmic structures, but rather an active participant in their evolution. The gravitational forces at play within the wall, combined with the broader forces of cosmic expansion, have shaped the wall's immense size and structure. The interaction between these forces, dark matter, dark energy, and gravity, continues to drive the evolution of the wall and other large-scale cosmic structures. Understanding how the Sloan Great Wall fits into the expanding universe will provide crucial information about the long-term evolution of the cosmos and the forces that shape it. Looking ahead, the study of large-scale cosmic structures like the Sloan Great Wall will continue to play a critical role in our understanding of the expanding universe. As new observational tools and advanced simulations become available, scientists will be able to map the universe in even greater detail, providing deeper insights into the forces that govern cosmic expansion and structure formation. The James Webb Space Telescope, Square Kilometre Array, and future gravitational wave detectors will be instrumental in expanding our knowledge of the universe's most massive features, shedding light on the role of cosmic expansion, dark matter, and dark energy in shaping the universe. The Sloan Great Wall and the fate of cosmic structures. As we continue to uncover more about large-scale structures like the Sloan Great Wall, it becomes increasingly clear that these colossal cosmic features hold the key to understanding the fate of the universe. The vastness of the wall, spanning 1.3 billion light-years, raises important questions about the long-term behavior of the universe and the role that such immense structures will play in its future. How will the Sloan Great Wall evolve? Will it eventually dissipate, merge with other structures, or even collapse under the influence of gravity? These questions challenge our current understanding of the universe's destiny and point to a need for more research into the long-term behavior of the cosmic web. One of the most fundamental aspects of the Sloan Great Wall is its composition. A long filament of galaxies connected by invisible dark matter filaments. This alignment of galaxies stretches over vast distances and represents a small but significant part of the larger cosmic web. The future of this structure is closely tied to the behavior of both dark matter and dark energy, two forces that we are only beginning to fully understand. While dark matter holds galaxies together through gravitational pull, dark energy accelerates the expansion of the universe, pushing galaxies farther apart over time. The interaction between these two forces will play a crucial role in determining whether large structures like the Sloan Great Wall continue to evolve as we see them today, or undergo dramatic changes in the distant future. The most immediate impact of these forces on the Sloan Great Wall is the effect of cosmic expansion. As the universe expands, galaxies are moving farther away from each other, and large-scale structures like the Sloan Great Wall are being stretched. However, this expansion is not uniform. The gravitational pull of dark matter helps to counteract the effect of cosmic expansion in certain regions, allowing structures like the Sloan Great Wall to persist. This interplay between dark matter and cosmic expansion raises important questions about the future of such filaments. Will they continue to exist as they are now, or will the expansion of the universe eventually cause them to break apart? Another key factor in the evolution of the Sloan Great Wall is the possibility of mergers with other large structures. As the universe evolves, cosmic structures like superclusters and galactic filaments are often drawn together by gravitational forces, leading to mergers that can dramatically reshape the landscape of the universe. The Sloan Great Wall, with its vast size and complex structure, could eventually merge with other nearby filaments and form an even larger cosmic structure. These mergers could result in the formation of new galaxies, new clusters, and perhaps even new superstructures that dominate the cosmic web. However, while mergers and the continued influence of dark matter and gravity may help sustain large-scale structures like the Sloan Great Wall for billions of years, there is a limit to how long these structures can persist. The future of the Sloan Great Wall is also bound to the fate of the universe itself. Current models of cosmic evolution suggest that the universe will continue expanding for the foreseeable future. This expansion, driven by dark energy, will eventually lead to the end of cosmic structures as we know them. In the distant future, as dark energy continues to accelerate the expansion of the universe, the fate of structures like the Sloan Great Wall may be sealed. As galaxies move farther apart, even the most massive structures will be torn apart by the forces of cosmic expansion. The Sloan Great Wall could eventually break into smaller pieces, each galaxy moving farther away from its neighbors as the universe continues to expand. Over time, the cosmic web may become more and more diffuse, with galaxies scattered across an ever-expanding universe. But what of the fate of the Milky Way and other galaxies in the Sloan Great Wall's vicinity? Will they simply drift apart, or will there be a larger cosmic event that will alter their path? The future of our galaxy, as well as other galaxies within the wall, is still uncertain. The cosmic web is not a static structure, and its evolution depends on complex interactions between galaxies, dark matter, and dark energy. As the universe continues to expand, the interactions between these forces will shape the future of the Sloan Great Wall and other large-scale structures. One of the more dramatic possibilities is that, in billions of years, the Milky Way and the Andromeda galaxy, which is located nearby, will collide and merge. This will not only change the future of our galaxy, but could also have a significant impact on other galaxies in the Sloan Great Wall. Galaxy mergers are not uncommon in the universe, and the collision between the Milky Way and Andromeda is expected to produce a new, larger galaxy, one that could potentially absorb neighbouring galaxies in the process. This scenario represents one of the most significant transformations a galaxy can undergo, and it raises the question of whether the Sloan Great Wall could eventually become a single, giant galaxy over time. Another possibility involves the decay of galactic filaments. Over billions of years, the influence of dark matter and dark energy will continue to pull at the fabric of large structures like the Sloan Great Wall, eventually leading to the disintegration of the wall itself. This disintegration could occur in stages, with galaxies breaking off and drifting apart as the forces of cosmic expansion gradually overcome the gravitational pull of dark matter. The final fate of the Sloan Great Wall could see it transformed into a more dispersed structure, possibly contributing to the formation of smaller, isolated galaxy clusters scattered throughout the universe. In the far future, once the influence of dark energy reaches its maximum, we could find ourselves in a universe dominated by dark energy, where the expansion of the universe is so rapid that galaxies, stars, and even atoms will be pulled apart by the overwhelming force. If the Sloan Great Wall still exists at that point, it will likely be unrecognizable, fragmented, and stretched across an ever-expanding universe. The universe could ultimately become a cold, empty expanse, with no remaining structure or matter to hold things together. Here are the three sections expanded with 200 additional words smoothly integrated into each. The role of galaxy surveys in mapping large-scale structures. The discovery of the Sloan Great Wall has had profound implications not only for observational astronomy, but also for cosmological simulations. The massive scale of the wall, extending over 1.3 billion light-years, challenges existing models of large-scale cosmic structure and provides new opportunities to refine our understanding of how galaxies form and evolve within the cosmic web. As we develop more advanced simulations of the universe's structure, the Sloan Great Wall has become a crucial test case for improving our models of galaxy distribution, cosmic flows, and dark matter's role in the formation of large-scale features. One of the primary goals of cosmological simulations is to model the distribution and motion of galaxies across vast regions of space. These simulations rely heavily on dark matter to explain how galaxies cluster together, form filaments, and interact. The discovery of the Sloan Great Wall has forced astronomers to rethink how galaxies and large-scale structures are organized. While earlier models suggested a more homogeneous distribution of galaxies, the Sloan Great Wall's sheer size and linearity have revealed that large structures like this one form through gravitational interactions, dark matter's influence, and other cosmic forces. The cosmic web, of which the Sloan Great Wall is a prominent feature, is made up of vast filaments of galaxies and dark matter, with large voids in between. To simulate these structures, cosmologists use n-body simulations, which model the behavior of particles, in this case galaxies and dark matter, under the influence of gravity. These simulations allow astronomers to trace the paths of galaxies over time, simulating how they would move and interact within the cosmic web. The results of these simulations have been instrumental in refining our understanding of large-scale structure formation. The discovery of the Sloan Great Wall has provided valuable data for these simulations. The wall's size, shape, and alignment with dark matter filaments serve as a real-world test case for the predictions made by cosmological models. By comparing the results of simulations with the actual structure of the Sloan Great Wall, astronomers can fine-tune their models to better match the observed universe. These models help scientists understand the role of dark matter in shaping the cosmic web, and they also provide insights into the cosmic flows that contribute to the evolution of large-scale structures. However, it's not just about measuring the distribution of galaxies. The study of large-scale cosmic structures through galaxy surveys helps astronomers investigate the interactions between galaxies and their surrounding environments. Understanding how these structures evolve and interact is crucial for predicting the future dynamics of the universe. As galaxies collide, merge, or move along the filaments, new patterns of interaction emerge that can reshape the cosmic web. These interactions also provide insight into how matter behaves on extremely large scales, as galaxies are often interconnected by dark matter, which exerts gravitational influence that shapes the entire cosmic network. Galaxy surveys have evolved dramatically in their methodology and scope over the past few decades. Modern surveys employ sophisticated spectroscopic techniques that not only identify galaxy positions, but also measure their redshifts with remarkable precision, allowing astronomers to construct detailed three-dimensional maps of cosmic structure. The Sloan Digital Sky Survey pioneered the use of multi-object spectrographs, which can simultaneously capture the spectra of hundreds of galaxies in a single observation. This technological breakthrough made it possible to map millions of galaxies efficiently, revealing structures like the Sloan Great Wall that would have remained hidden in earlier two-dimensional surveys. The integration of photometric and spectroscopic data has created a comprehensive picture of galaxy properties, including their ages, compositions, and star formation rates, all of which provide crucial context for understanding how the wall assembled over cosmic time. Furthermore, the analysis of galaxy surveys has benefited enormously from advances in machine learning and artificial intelligence. These computational tools can identify subtle patterns in vast datasets that might escape human detection, revealing connections between galaxies that traditional analysis methods might miss. Algorithms trained on simulated data can recognize the signatures of specific formation processes, helping astronomers distinguish between different theoretical scenarios for how structures like the Sloan Great Wall came into being. The combination of observational data with machine learning techniques has opened new avenues for discovery, enabling researchers to extract maximum scientific value from survey data and to identify candidate regions for follow-up observations with more powerful telescopes. Another important aspect of the Sloan Great Wall is its potential to shed light on the role of cosmic voids, the vast empty regions of space that exist between the filaments of galaxies. While these voids may seem insignificant at first glance, they play a critical role in shaping the universe. Cosmological simulations that incorporate voids are crucial for understanding how galaxies are distributed and how large-scale structures like the Sloan Great Wall form. Voids are not empty spaces, but rather regions of space where gravitational forces are weaker, allowing galaxies to move freely and influencing the formation of galaxy filaments. Simulations that model these interactions provide a more complete picture of the universe's structure. The study of dark matter and dark energy also benefits from these large-scale surveys. Dark energy is the force responsible for the accelerated expansion of the universe, and understanding how it interacts with dark matter can help scientists better comprehend the forces shaping the universe. By analysing the Sloan Great Wall, astronomers can examine how dark energy has influenced the expansion of cosmic structures, both at the galactic scale and across large cosmic filaments. This also opens up the possibility of studying the expansion rate of the universe more accurately, which is a crucial step in understanding the ultimate fate of the cosmos. The increasing size and sophistication of these galaxy surveys have made them invaluable tools for understanding the Sloan Great Wall and other large-scale structures. These surveys now cover millions of galaxies, and their data is essential for understanding the dynamics of cosmic filaments. For instance, the SDSS has helped astronomers track the movements of galaxies within the Sloan Great Wall, providing a detailed picture of how gravitational forces shape the structure. In addition, surveys like the Dark Energy Survey, DES, and Pan-STARRS are actively exploring the effects of dark energy on the universe's expansion, shedding light on how it influences large-scale structures. The future of galaxy surveys looks promising. The Square Kilometre Array, SKA, set to be the world's largest radio telescope, will play a pivotal role in mapping the universe's largest structures. The SKA will be able to observe galaxies and cosmic structures in greater detail than ever before, providing insights into how large-scale features like the Sloan Great Wall formed, and how they will evolve over time. Additionally, upcoming missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will continue to expand our ability to study galaxies and cosmic structures across different wavelengths of light, enabling us to peer deeper into the universe than ever before. The sheer amount of data produced by these surveys, combined with advancements in computational astrophysics, will help astronomers refine their models of the universe and gain a more detailed understanding of how large-scale structures like the Sloan Great Wall fit into the cosmic web. As our observational capabilities continue to improve, the potential for new discoveries is vast, and it's likely that the Sloan Great Wall will not remain the largest known structure in the universe for long. As we continue to probe deeper into the cosmos, more astonishing features are sure to be discovered, reshaping our understanding of the universe and our place within it. The role of the Sloan Great Wall in cosmological simulations. The discovery of the Sloan Great Wall has had profound implications not only for observational astronomy, but also for cosmological simulations. The massive scale of the wall, extending over 1.3 billion light-years, challenges existing models of large-scale cosmic structure and provides new opportunities to refine our understanding of how galaxies form and evolve within the cosmic web. As we develop more advanced simulations of the universe's structure, the Sloan Great Wall has become a crucial test case for improving our models of galaxy distribution, cosmic flows, and dark matter's role in the formation of large-scale features. One of the primary goals of cosmological simulations is to model the distribution and motion of galaxies across vast regions of space. These simulations rely heavily on dark matter to explain how galaxies cluster together, form filaments, and interact. The discovery of the Sloan Great Wall has forced astronomers to rethink how galaxies and large-scale structures are organized. While earlier models suggested a more homogeneous distribution of galaxies, the Sloan Great Wall's sheer size and linearity have revealed that large structures like this one form through gravitational interactions, dark matter's influence, and other cosmic forces. The cosmic web, of which the Sloan Great Wall is a prominent feature, is made up of vast filaments of galaxies and dark matter, with large voids in between. To simulate these structures, cosmologists use n-body simulations, which model the behavior of particles, in this case, galaxies and dark matter, under the influence of gravity. These simulations allow astronomers to trace the paths of galaxies over time, simulating how they would move and interact within the cosmic web. The results of these simulations have been instrumental in refining our understanding of large-scale structure formation. The discovery of the Sloan Great Wall has provided valuable data for these simulations. The wall's size, shape, and alignment with dark matter filaments serve as a real-world test case for the predictions made by cosmological models. By comparing the results of simulations with the actual structure of the Sloan Great Wall, astronomers can fine-tune their models to better match the observed universe. These models help scientists understand the role of dark matter in shaping the cosmic web, and they also provide insights into the cosmic flows that contribute to the evolution of large-scale structures. The Sloan Great Wall is an excellent example of the power of cosmological simulations. The wall is a massive, long and linear feature that could only have formed under specific conditions involving dark matter and gravitational forces. Simulations that accurately model these conditions allow scientists to understand the forces at play and how they interact over time. The presence of large-scale structures like the Sloan Great Wall suggests that galaxy formation and cosmic evolution are far more complex than previously thought. Modern cosmological simulations have reached unprecedented levels of sophistication, incorporating not just dark matter dynamics, but also the complex physics of baryonic matter, the ordinary matter that makes up stars, gas, and planets. These hydrodynamic simulations track how gas cools, condenses, and forms stars within dark matter halos, capturing the intricate feedback processes that regulate galaxy formation. Supernova explosions and active galactic nuclei can blow gas out of galaxies, temporarily halting star formation and redistributing matter across vast distances. When applied to structures like the Sloan Great Wall, these simulations reveal how the interplay between dark matter, gravitational assembly, and baryonic physics produces the diverse galaxy populations we observe. Some simulations have successfully reproduced wall-like structures with properties remarkably similar to the Sloan Great Wall, lending credibility to our theoretical understanding while also highlighting discrepancies that point toward missing physics or incomplete models. The computational demands of these simulations are staggering. Simulating a volume large enough to contain structures like the Sloan Great Wall while maintaining sufficient resolution to track individual galaxies requires tracking billions or even trillions of particles over cosmic time. This has driven innovation in computational techniques, including adaptive mesh refinement, which focuses computational resources on regions of high density, and parallel computing algorithms that distribute calculations across thousands of processors. The illustrious Eagle and Millennium simulations represent landmark achievements in this field, each pushing the boundaries of what's computationally feasible. These simulations generate synthetic universes that can be directly compared with observations, allowing researchers to test whether our theoretical framework, dominated by cold, dark matter and dark energy, can account for the observed cosmic structure, including anomalies like the unexpectedly large scale of the Sloan Great Wall. Another important aspect of the Sloan Great Wall is its potential to shed light on the role of cosmic voids, the vast, empty regions of space that exist between the filaments of galaxies. While much attention has been paid to the dense, interconnected regions of the cosmic web, the voids play a significant role in shaping the universe. Cosmological simulations that incorporate voids are crucial for understanding how galaxies are distributed and how large-scale structures like the Sloan Great Wall form. Voids are not empty spaces, but rather regions of space where gravitational forces are weaker, allowing galaxies to move freely and influencing the formation of galaxy filaments. Simulations that model these interactions provide a more complete picture of the universe's structure. As our computational power continues to grow, simulations will become increasingly sophisticated. New technologies and advanced techniques in supercomputing will allow astronomers to run larger, more detailed simulations that incorporate a wider range of variables, from dark energy to the behavior of galaxy clusters. These simulations will be critical for understanding not only the Sloan Great Wall, but also other large-scale structures in the universe. With the help of these simulations, astronomers will be able to study the formation and evolution of cosmic filaments, superclusters, and voids in greater detail than ever before. The role of the Sloan Great Wall in these simulations is also valuable for exploring the future of the universe. Cosmic simulations are not only concerned with the past, but also with projecting the future. By simulating the behavior of large-scale structures over billions of years, astronomers can make predictions about how structures like the Sloan Great Wall will evolve. Will the wall continue to exist in its current form, or will it eventually break apart due to the influence of dark energy? Will its galaxies continue to cluster together, or will they disperse due to the accelerating expansion of the universe? These simulations provide essential insights into the long-term fate of the universe and the large-scale structures within it. In the coming decades, the advancement of cosmological simulations will offer even more remarkable insights into the nature of large-scale structures like the Sloan Great Wall. As we continue to observe the universe and gather more data, simulations will play an increasingly important role in interpreting these observations. The combination of observational data, cosmological simulations, and theoretical models will help scientists refine their understanding of how the universe works and how structures like the Sloan Great Wall fit into the larger cosmic picture. In conclusion, the Sloan Great Wall has not only expanded our understanding of large-scale cosmic structures, but also played a pivotal role in refining cosmological simulations. By serving as a real-world test case for the distribution and movement of galaxies, the Sloan Great Wall provides valuable data that helps improve our models of the universe. As technology continues to advance, the role of simulations in understanding the cosmic web and the evolution of structures like the Sloan Great Wall will become even more critical, offering deeper insights into the forces that govern the universe and its ultimate fate. Future discoveries and the legacy of the Sloan Great Wall. As the universe continues to reveal its secrets, the Sloan Great Wall will undoubtedly remain a focal point in the study of large-scale structures and the broader cosmic web. The discovery of this colossal structure has already reshaped our understanding of the universe, and as new technologies and research methods evolve, we are likely to uncover even more about its true nature. The ongoing study of the Sloan Great Wall not only informs our knowledge of galaxy formation, but also deepens our understanding of the fundamental forces that govern the cosmos. One of the most exciting possibilities for future discoveries surrounding the Sloan Great Wall lies in the continued advancement of observational technologies. Telescopes and observatories, both on Earth and in space, are becoming more powerful, allowing astronomers to observe increasingly distant and faint objects. Instruments like the James Webb Space Telescope, JWST, which is set to provide incredibly detailed images and data on galaxies and large-scale structures, will likely offer a wealth of new information on the Sloan Great Wall and similar cosmic features. JWST's ability to observe in the infrared spectrum will provide insights into previously hidden parts of the cosmos, allowing astronomers to study the earlier stages of galaxy formation and the interactions between dark matter and visible galaxies. In addition to the James Webb Space Telescope, future radio observatories such as the Square Kilometre Array, SKA, will revolutionize our understanding of large-scale structures. The SKA, which will be capable of observing the universe in low-frequency radio waves, will allow scientists to map the distribution of neutral hydrogen, one of the most abundant elements in the universe, across vast regions of space. This will provide unprecedented insight into the formation and distribution of galaxies and galaxy clusters, offering a deeper understanding of how structures like the Sloan Great Wall evolved. As we continue to collect more data from these cutting-edge observatories, one of the main challenges will be to interpret and model the vast amounts of information they generate. The Sloan Great Wall serves as an invaluable test case for how astronomers interpret large-scale cosmic structures. The sheer scale of the wall, with its billions of galaxies and intricate web of dark matter filaments, demands that our models become more sophisticated and more nuanced. As computational power continues to grow, the ability to simulate and analyze these structures will provide new insights into the mechanics of the universe. The legacy of the Sloan Great Wall extends beyond its physical dimensions to its role as a catalyst for methodological innovation in astronomy. Its discovery demonstrated the power of large-scale collaborative surveys, where thousands of individual observations are synthesized into coherent maps of cosmic structure. This approach has now become standard practice, informing the design of next-generation surveys that will probe even deeper into space and time. The techniques developed to analyze the Sloan Great Wall, including statistical methods for identifying overdensities, algorithms for tracing filamentary structures, and frameworks for comparing observations with simulations, have been adopted across the field and applied to diverse problems in astrophysics. Future surveys will build on this foundation, employing multi-wavelength observations that combine optical, infrared, radio, and X-ray data to create the most comprehensive view of cosmic structure ever achieved. Moreover, the Sloan Great Wall has inspired new theoretical frameworks for understanding structure formation. The wall's existence at the upper limits of what standard cosmological models predict has prompted researchers to explore whether modifications to our theories might be necessary. Some scientists have proposed that the wall could be evidence of non-Gaussian initial conditions in the early universe, or that it reflects the influence of primordial density fluctuations on scales larger than previously considered significant. Others suggest that the wall's properties might reveal subtle effects of dark energy that operate differently on different scales, or that it could provide clues about the nature of inflation, the rapid expansion thought to have occurred in the universe's first fraction of a second. These theoretical explorations sparked by the wall's discovery continue to push the boundaries of cosmological theory and may ultimately lead to a deeper understanding of the universe's fundamental nature and evolution. One area of particular interest will be the study of dark energy and its role in the formation and evolution of structures like the Sloan Great Wall. As the universe expands at an accelerating rate, understanding how dark energy interacts with the cosmic web is crucial. Dark energy is thought to be the force responsible for the accelerated expansion of the universe, and its influence is likely to affect large-scale structures like the Sloan Great Wall. As astronomers and physicists continue to study dark energy through increasingly precise measurements, the relationship between this mysterious force and cosmic structures will become clearer, helping us refine our models of the universe. Moreover, as our observational capabilities expand, we may begin to detect new and even larger cosmic structures, further challenging our current understanding. The Hercules Corona Borealis Great Wall, which was discovered in 2013 and is considered the largest known structure in the universe, could provide important comparisons for understanding the Sloan Great Wall's formation and evolution. These new discoveries will force us to continually adjust our models of how galaxies are distributed and how large-scale structures form and evolve over time. In addition to large-scale structures, the study of galaxy mergers and galactic evolution will remain a critical aspect of understanding the universe. The interaction between galaxies within the Sloan Great Wall, as well as their eventual fate, will provide key insights into how galaxies grow, collide, and eventually evolve into larger structures. These galactic interactions are a central part of cosmic evolution, and understanding them can help us predict how the universe will continue to evolve in the future. The cosmic web is not a static feature of the universe. It is a dynamic, ever-evolving structure that changes over time. The Sloan Great Wall itself may evolve as galaxies move, interact, and merge. These dynamic processes will continue to reshape the structure of the universe, and the data we gather from future surveys and simulations will help us better understand these changes. The potential for new discoveries in the coming years is vast, and the Sloan Great Wall will continue to serve as a crucial piece of the cosmic puzzle. In conclusion, the legacy of the Sloan Great Wall lies not only in its immense size, but in the way it has fundamentally changed our understanding of the universe. Its discovery has prompted a re-evaluation of how galaxies are distributed and how large-scale structures form. With the continued advancement of observational technologies and computational simulations, we are likely to uncover even more about the nature of the Sloan Great Wall and other similar structures. These discoveries will deepen our understanding of the universe's vastness, its underlying forces, and our place within it. As we push the boundaries of scientific knowledge, the Sloan Great Wall will remain a symbol of the incredible complexity and beauty of the cosmos. The ongoing study of this colossal structure, along with the insights it provides into the evolution of the universe, will continue to shape our understanding of the cosmos for generations to come. The future of large-scale cosmic structures. What lies ahead? The Sloan Great Wall has significantly expanded our understanding of the cosmic web, a vast network of galaxies and structures connected by dark matter filaments that define the universe's grand architecture. Yet, while it offers a glimpse into the immense scale of the universe, it also raises crucial questions about the future of large-scale structures in cosmology. The discovery of the Sloan Great Wall, alongside other similar structures like the Hercules Corona Borealis Great Wall, signals that there may be far more massive structures waiting to be discovered. So, what does the future hold for the study of these colossal cosmic formations? And how will they shape our understanding of the universe's evolution? To begin with, the continued expansion of the universe will have a profound effect on the fate of large-scale cosmic structures like the Sloan Great Wall. Current models of cosmic expansion suggest that dark energy, the mysterious force accelerating the expansion, will continue to dominate the universe's behavior. As the universe expands, galaxies are moving away from each other at an accelerating rate. Over billions of years, this expansion will likely cause large-scale structures, including filaments like the Sloan Great Wall, to spread out and become less dense. As galaxies drift further apart, the intricate web of galaxies may lose its current form, leading to the eventual dissolution of features like the Sloan Great Wall. However, even as cosmic expansion continues, the impact of dark matter and gravitational forces may ensure that some large-scale structures persist. While dark energy pushes galaxies apart, dark matter's gravity works to bind them together, especially in regions of high density like galaxy clusters and filaments. The influence of dark matter may continue to hold structures like the Sloan Great Wall together for an extended period, even as the universe itself expands. This gravitational pull is particularly significant in the dense regions of the cosmic web, where galaxies are more tightly packed. As a result, some parts of the Sloan Great Wall may survive much longer than others, even as the universe's expansion causes the rest of the cosmic web to disperse. Additionally, the study of large-scale cosmic structures will continue to benefit from advancements in observational technology. The James Webb Space Telescope, JWST, is poised to revolutionize our ability to observe the universe in greater detail, especially in the infrared spectrum. With its advanced instruments, The JWST will allow astronomers to study galaxies and cosmic structures that are far beyond the reach of previous telescopes. This will provide more precise measurements of the distribution of galaxies and dark matter in large-scale structures like the Sloan Great Wall, offering deeper insights into their formation, evolution, and eventual fate. Other upcoming missions, such as the Euclid mission from the European Space Agency, will focus on studying the distribution of dark matter and dark energy across the cosmos. These missions will help scientists understand how the forces of gravity and dark energy work together to shape structures like the Sloan Great Wall. By mapping the distribution of dark matter and studying the expansion of the universe, astronomers will be able to make more accurate predictions about the long-term behaviour of large-scale structures. Simultaneously, computer simulations will continue to play a critical role in our understanding of cosmic structures. With the help of supercomputing and more refined models of gravity, dark matter, and dark energy, scientists will be able to simulate the future evolution of structures like the Sloan Great Wall. These simulations will take into account a wide range of factors, from the motion of galaxies to the influence of dark energy, allowing scientists to predict how these structures will evolve over the next billions of years. By combining observational data with advanced simulations, astronomers will be able to piece together a more complete picture of the future of the universe. Moreover, as our ability to detect and observe large-scale cosmic structures improves, we may discover even more massive features in the universe. The Sloan Great Wall, once considered the largest known structure in the observable universe, may eventually be surpassed by other, even more massive filaments and superclusters. The vastness of the universe suggests that there are still countless discoveries waiting to be made. As we improve our technology and deepen our understanding of the cosmos, new structures will likely emerge, challenging our current models and expanding our view of the universe's architecture. In the more distant future, as the universe continues to expand, we may see the emergence of new forces at play. Galaxy mergers, gravitational wave interactions, and the ongoing influence of dark matter could shape the universe in ways we cannot yet predict. While we are only beginning to understand the fundamental forces that govern large-scale structures, it is clear that the future of these structures, including the Sloan Great Wall, is closely tied to the ongoing evolution of the universe itself. The cosmic web is not a static feature, but rather a dynamic and ever-changing network that evolves over time. As new observational tools and simulation techniques continue to advance, our understanding of the universe's large-scale structure will evolve as well. While the Sloan Great Wall's future may be uncertain, its legacy will continue to shape the way we study and understand the universe for generations to come. In conclusion, the Sloan Great Wall offers a window into the vast, interconnected network that makes up our universe. As we look to the future, we can expect more discoveries that challenge our understanding of the cosmos and provide deeper insights into the formation, evolution, and fate of these monumental structures. The continued study of large-scale cosmic structures, along with advancements in technology and simulation, will help scientists refine their models of the universe and answer some of the most fundamental questions about the forces that shape the cosmos.